Hi, I'm Lak, and I lead a team that helps customers of Google Cloud successfully build applications that use our big data and machine learning products. Among the things we do is to create big data and machine learning training courses and labs, like this course, Big Data and Machine Learning Fundamentals with Google Cloud Platform. This course was designed to showcase real-world data and ML challenges and give you practical hands-on expertise in solving those challenges using Google Cloud. It's a critical course to master because it covers the most common use cases you and your team will encounter on your big data journey. This course is divided into 6 content modules. In the first module, which is on data-driven decision making, you will learn all about the data and ML tools available on GCP from a high-level organizational perspective. And then, in the next 4 modules, you will be introduced to Google Cloud products in context as they're employed to solve real-world problems. In the 4 modules, in addition to expanding your knowledge about our products and platform, you will also get to practice with hands-on quick labs. Finally, in the summary module, we'll do a recap of everything you've learned in this course and provide you with additional resources on the topics that you've done. In each module, this is the typical order we'll follow. First, we'll have lectures from subject matter experts where we'll introduce the big data scenario and the associated challenges and how to address them with cloud technologies. Next, you'll see a demo of the solution in action, which will highlight key features that you will learn and practice in your labs. After you understand the scenarios and have watched the demos, it's time for you to practice with quick labs in a real Google Cloud Platform account. Finally, you will explore real customer use cases and architectures so you can familiarize yourself with best practices and get inspired in your own solutions. In other words, we describe a common class of big data and ML problems and hone in on one specific problem. And then we show you a demo of a solution to that problem. And then we talk about why we built the solution that way, using that opportunity to cover how and when to use the various products used in the solution. Finally, we widen the lens and show you real-world applications that are variants of the principles covered in the chapter. You're already taking this course, which means you recognize the importance of big data processing. But why is this skill set in such high demand? According to McKinsey research, by 2020, we'll have 50 billion devices connected in the Internet of Things. These devices will cause the supply of data to double every 2 years. Unfortunately, though, only about 1% of the data generated today is actually analyzed, according to McKinsey. This state of affairs provides a wide open opportunity because there's a lot of value in data. I believe that the ability to build applications that handle large amounts of data and derive insights from that data in an automated manner, this ability is a skill that will be well rewarded in the marketplace. Individuals who have this skill will have many opportunities open to them, and companies that develop this skill will become more successful. So the opportunity for data analysts, data scientists, and data engineers, we'll talk about what these roles are and what the differences are. The opportunity for all 3 of these roles is very clear. At its core, this course is primarily geared towards data engineers. That said, if you're an analyst, an ML engineer, or a tech lead for your team, it's a valuable skill to know how all the big data and ML products interact to solve some of the most common challenges that data engineers face. And what are those challenges? Those challenges are migrating your existing big data workloads to an environment where you can effectively analyze all of your data. Interactively analyzing large, and by large I mean terabytes to petabytes, analyzing large data sets of historical data. Third, building scalable pipelines that can handle streaming data so that your business can make data-driven decisions more quickly. And finally, building machine learning models so that you're not just reacting to data, you're able to make predictive, forward-looking actions using your data. Hi, I'm Lak. Welcome to the first module of our Big Data Fundamentals course. It provides an introduction to Google Cloud Platform. In this module, we'll examine the infrastructure behind Google Cloud Platform, or GCP, which was originally built to power Google's own applications and is now available to you. Then, we'll cover the big data and ML products that are built on top of that infrastructure and when you should choose which products for your solution architecture. After that, my favorite part of this course, learning from other customers who are using Google Cloud by exploring their use cases and getting inspired to solve similar challenges for your own teams and projects. You will learn where you can look up reference case studies of GCP customers by industry or by product. And then you'll examine their solution architecture in a short activity. Building the right team structure is critical to solving these big data challenges. We'll explore the different types of roles and personas for building a successful big data team within your organization. Consider for a second the impact that Google Search has on our daily lives with timely and relevant responses. Now think of other Google products: Gmail, Google Maps, Chrome, YouTube, Android, Play, Drive. Each of these products has over 1 billion monthly users. Google has had to develop the infrastructure to ingest, manage, and serve all the data from these applications, and to do so with a growing user base and data requirements that are constantly evolving. 7 products with 1 billion users. Actually, there's an 8th Google product that has 1 billion end users. Google Cloud except that it's your users. The end users served by Google Cloud customers such as Home Depot and Spotify, Twitter and New York Times, Colgate-Palmolive and Gojek. Let's look at the building blocks behind Google's big data infrastructure and how you can leverage it with Google Cloud. There are 4 fundamental aspects of Google's core infrastructure and a top layer of products and services that you will interact with most often. The base layer that covers all of Google's applications, and therefore Google Cloud's too, is security. On top of that are compute, storage, and networking. These allow you to process, store, and deliver business-changing insights, data pipelines, and machine learning models. Finally, while running your big data applications on bare metal virtual machines is possible, Google has developed the top layer of big data and ML products to abstract away a lot of the hard work of managing and scaling that infrastructure for you. A growing data organization like yours will need lots of compute power to run big data jobs, especially as you design for the future so that you can outpace the growth in new users and data for the next decade. Let's start with an example illustrating how Google uses its own compute power. Google Photos has recently been introducing smart features like this one for automatic video stabilization, for when the camera is shaky, as you see here on the left. What data sources do you think are needed as inputs to the model? Well, you need the video data itself, which is essentially lots of individual images called frames ordered by timestamps. But we also need more contextual data than just the video itself, right? Absolutely. We need time series data on the camera's position and orientation from the onboard gyroscope and motion on the camera lens. So, how much video data are we talking about for the Google Photos ML model to compute and stabilize these videos? If you consider the total number of floating point values representing a single frame of high-res video, it's a product of the number of channel layers multiplied by the area of each layer, which with modern cameras can easily be in the millions. An 8 megapixel camera creates images of 8 million pixels each, approximately. Multiply that by 3 channel layers, and you get over 23 million data points per image frame. And there are 30 frames per second of video. And you can quickly see how a short video becomes over 1 billion data points to feed into the model. And from 2018 estimates, roughly 1.2 billion photos and videos are uploaded to the Google Photos service every day. That is 13 plus petabytes of photo data in total. For YouTube, which also has machine learning models for video stabilization and other models for automatically transcribing audio, you're looking at over 400 hours of video uploaded every minute. That's 60 petabytes every hour. But it's not just about the size of each video in pixels. The Google Photos team needed to develop, train, and serve a high-performing machine learning model on millions of videos to ensure that the model is accurate. That's the training dataset for this one feature. Just as your laptop hardware may not be powerful enough to process a big data job for your organization, a phone's hardware is not powerful enough to train sophisticated machine learning models. Google trains its production machine learning models on its vast network of data centers and then deploys smaller trained versions of these models to the hardware on your phone for predictions on new video. A common theme throughout this course is that when Google makes breakthroughs in AI research, it continues to invest in new ways to expose these as fully trained models for everyone. You can therefore leverage Google's AI research with pre-trained AI building blocks. For example, if you're a company producing movie trailers and quickly want to detect labels and objects in thousands of these movie trailers to build a movie recommendation system, you could use a Cloud Video Intelligence API. You could use that API instead of building and training your own custom model. There are other fully trained models for language and for conversation too. You will learn and practice using these AI building blocks later in this course. But getting back to the Google Photos machine learning story, running that many sophisticated ML models on large structured and unstructured datasets for Google's own products required a massive investment in computing power. That's why Wired says, this is what makes Google Google. Its physical network, its thousands of fiber miles, and those many thousands of servers that in aggregate add up to the mother of all clouds. In essence, Google has been doing distributed computing for over 10 years for its own applications, and now has made that compute power available to you through Google Cloud. But simply scaling the raw number of servers in Google's data centers isn't enough. Here's an interesting rough calculation by Jeff Dean, who leads Google's AI division. He realized years ago that if everybody wanted to use voice search on their phones and used it for only 3 minutes, we would need to double our computing power. Historically, compute problems like this could be addressed through Moore's Law. Moore's Law was a trend in computing hardware that described the rate at which computing power doubled. For years, computing power was growing so rapidly that you could simply wait for it to catch up to the size of your problem. Although computing power was growing rapidly even as recently as 8 years ago, in the past few years, growth has slowed dramatically as manufacturers run up against fundamental physics limits. Compute performance has hit a plateau. One solution is to limit the power consumption of a chip. And you can do that by building application-specific chips or ASICs. And one kind of application is machine learning. Google's designed new types of hardware specifically for machine learning. The Tensor Processing Unit, or TPU, is an ASIC specifically optimized for ML, and it has more memory and a faster processor for ML workloads than traditional CPUs or GPUs. Google has been working on the TPU for several years and has made it available to other businesses like yours through Google Cloud for really big and challenging machine learning problems. One such business that uses TPUs is eBay. They use cloud TPU pods to deliver faster inferences of predictions, faster inferences to their users by a factor of 10. That's a 10x speed up. The decrease in model training time has also led to faster model experimentation. ML model training and feature engineering is one of the most time-consuming parts of any machine learning project. eBay's VP of New Product Development remarked that the additional memory of the TPU pods enabled them to improve their turnaround time and iterate faster. One last example of compute power at Google and an inside look at our culture of thinking 10x is how our teams used machine learning to boost Google's own data center efficiency. The potential impact for machine learning was there, considering the number of data centers that Google has to keep cooled and powered, and we were already collecting streaming sensor data for our existing monitoring platforms. Engineers at Alphabet's DeepMind saw this as an opportunity to ingest that sensor data and train a machine learning model to optimize cooling better than existing systems could. The model they implemented reduced the cooling energy by 40% and boosted the overall power effectiveness by 15%. I find this example particularly inspirational because it's a machine learning model trained on machine learning specialized hardware in a data center, telling the data center how hot it can run the machine learning specialized that the model is training on. Powerful inception level stuff. Later in the course, you will see a demo on how you can set up a streaming data ingestion pipeline for your own IoT devices in less than an hour. So in this demo, I'm going to be showing you how to spin up a Compute Engine instance, run some software on it, copy files from that Compute Engine instance to cloud storage, and publish those files to make them public. The use case that we're going to be doing is to plot earthquake activity that happened in the previous week. And this data comes from USGS. So let me go ahead and go to cloud.google.com. So I'm starting on cloud.google.com, and I'll go to the Compute Engine part of it, go to VM instances, and create a VM. So I'll click Create here, and at this point, I'm creating a new virtual machine. Let's call it an Earthquake VM. Right? We can call it whatever we want. We can choose where in the world we want it. I happen to be closer to Oregon now, so I'll go ahead and do US West, and I'll pick a zone. I can pick US West B. Let me go ahead and say that I want to use 2 virtual CPUs. As you can see, we can at this point in time go up to about 64 CPUs with about 250 gigs of RAM. Another thing that I can do is I can click Customize and say that I want 18 CPUs and 50 gigs of RAM. Go find me a machine that matches these requirements. But in our case, what we'll do is we'll just go back and we'll pick a pretty small machine, like 1 GPU is probably enough. And then 10 gigs of space is enough. But of course, we can change that and we can use a different operating system with the different size of disk if we wanted. And we want to be able to use GSUtil, gcloud, etc. So I will allow full access to all my cloud APIs so that I can write to cloud storage from the VM. And I don't want to directly access the VM through HTTP or HTTPS. So we will just access it through SSH. So I'll go ahead and create the virtual machine. And at this point, the virtual machine is getting created. Let's wait a few seconds. And once the VM is up, we should be able to SSH into it. So there it is. Here's my VM. And at this point, this is a bare bones virtual machine that I'm SSHing into. This virtual machine, clear ls, so it doesn't have anything on it. In fact, it doesn't have even very basic software like Git. So if I were to type Git here, it says Git is not found. So I need to install Git. Good thing is we can do that, right? I have root access. And so what I can do is I can do sudo, which gives me root access, apt-get install Git. Okay. And it says, do you want to continue? Yes, I do. And this now installs Git, which is a way to access my source code repository, which contains everything else that I need. So I will go ahead and do git clone, https www.github.com, Google Cloud Platform. So this now gets the data from GitHub, gets all of the data that I need, including the files. And now if I do ls, I have my repository. And in this case, this is part of the files for this course. And so we can go into BDML fundamentals, and there is the earthquake VM. I'll go into the earthquake VM and look at what files are present. Turns out that I have an HTML file already. I have some a shell script to ingest data. I can do less ingest.sh. And this basically goes ahead and removes an existing earthquakes.csv and does a wget, which is a way to download data over HTTP from earthquake.usgs.gov and saves it as earthquakes.csv. So that's what ingest.sh does. But in order, then I also have transform.py, and transform.py basically is some Python code that uses matplotlib to go ahead and parse the earthquake data from USGS and put it on an earth map, creates a PNG out of it. So this particular file can be run to go ahead and process a weekly data from the USGS. It goes ahead and gets 1 week of data from USGS and creates earthquakes.png. In order to do that though, I need to have some software installed, and the software that I need, it's all listed in the installed missing.sh. So I need to basically get a bunch of different Python libraries. So let me go ahead and first run install missing.sh. This goes ahead and downloads and installs all of the Python packages that I need. As you can see, working with a virtual machine on the cloud is like working with any other Unix machine. In this case, because I created a Debian machine, I get a Unix machine, and that's a Unix machine that I'm working with. At this point, it has all the Python packages that I want. We can go ahead and say ingest.sh, and it will go ahead and download an earthquakes.csv. You can see that there's an earthquakes.csv now that's been created. And if we were to do head shows the first few lines of the file. It turns out that currently there has been an earthquake in California, and there has been another earthquake in Alaska, and so on, right? So let's go ahead. And so there's 93 kilometers east-northeast of Cape Yakataga, Alaska at the time that I'm recording this demo. So there's a bunch of earthquakes. We've gotten the data. But looking at a CSV file is not very interesting. Let's go ahead and create an image out of it. In order to do that, I will run transform.py. So transform.py is essentially getting the earthquake data, converting an image. And notice at this point, there's no image. But now if I do lsstar.png, I now have an earthquakes.png. So let's go ahead and now put it onto the cloud. We want to get rid of this virtual machine. The whole idea is compute and storage are separate. So we've done the compute. We have some files. Let's copy them off the machine into cloud storage so that we can delete the machine. Right? So let's go and create a cloud storage bucket. The way to do that is, again, go down here. And last time we did compute engine. This time we're going to do storage. So we'll go to storage browser and say that we want to create a bucket. Okay, so let's go ahead. I already created this bucket. Let me just delete that. I don't need that bucket. Let's say that I want to create a bucket, and I have to give my bucket a unique name. So let's say that I want to give the bucket the name earthquake, but the bucket name is already in use. A bucket name has to be globally unique. So I can say earthquake 2019, and I have it, right? So there is nobody else who's created a bucket of this name. If you can't come up with a unique name, try using a project name, right? This project name is also globally unique, and in many cases, that might work as well. An easy way to do that is we could go down to the home menu, and there is a project name. I can copy the project name, go back to the storage thing and say, can I create a bucket of that name? Yep, I can. So that also works. So I can create something with this particular name as my bucket. Let's make it multi-regional so we can access it from anywhere in the world. And it's going to cost us about 3 cents per gigabyte per month. And we can now choose how to set the permissions. Normally, you want to set permissions, but one object by object, right? But let's go ahead and specify it object by object. So we can go ahead and create the bucket. So now we've created a bucket with this name, and I'll copy that into my thing. And that bucket is now created. We can now come back to this virtual machine, and we can say gsutil ls and the name of the bucket. And it doesn't have anything in it right now. So it should be empty. So it doesn't have anything in it. What we can now do is I can have gsutil copy earthquakes.star to the bucket. So at this point, it's copied 3 files. It's copied the CSV file, the HTML file, and the PNG file. And indeed, when we come down here and we say refresh, we should have the 3 files. So hooray. So we have the 3 files. All 3 files currently are not public. So no one can access them except us because we own these files. But from this point onwards, I don't need the virtual machine. So let me just go down to the compute engine and say, hey, that virtual VM instances, select my virtual machine, and I can do one of 2 things. I can stop the virtual machine, in which case it's like pausing the VM. I'll be paying for the disk, but I won't be paying for the storage at all, right? The other thing that I can do, instead of stopping the VM, is that I can delete the VM, right? So I can go ahead and delete the VM. I don't need it ever again. So stopping is actually a very convenient way. We've installed a bunch of software. We don't want to get rid of the VM, but we don't want to pay for the compute of the VM. So what we could do is we could just stop it, right? So the VM is no longer running, and we can just say stop. And now the VM is paused. And at this point, right, once that VM is paused, we'll only get charged for that 10 gigs of disk that we had attached to the VM. So a relatively inexpensive way to have a virtual machine sitting around that has all of the software, everything that we have installed on it. If we ever need to run things again, we can come back, restart the VM, and run things. But let's go back to our storage. Okay. And you will see that the data here is private. And what we want to do is that we want to make it public. We want to make it accessible from anybody. What we could do is we could go down to the storage. And now we are in the bucket. And we can say that we want to take these 3 files, go to the permissions, okay, right? And we can say that we want to go to the permissions and we want to add members, and we can add a members called all users, okay, and give those users, everybody, storage object viewer. So they will be able to view that particular object. Okay. So now we have our all users, okay, and all users has a storage object viewer on these objects. So now if we go now, we see that these 3 things are public, and Google Cloud helpfully warns us that these 3 things are public. They all have public links associated with them. So we can actually go down here and say, what is a public link? Click on the link, and that is storageapis.googleapis.com. So anybody who comes to this particular link will be able to basically see the earthquakes this week. So this is, at this point, I'm recording it on March 28th. I'm recording it on April 4th. So the week started on March 28th. So I have 7 days of data. And these are the earthquakes that we saw in Alaska. And those are the earthquakes that we saw in California. And you can kind of see the ring of fire with all of these earthquakes that are happening around the coast of the Pacific. But to bottom line, what did we do? We spun up a virtual machine, we carried out processing on it, and then we took those files, we copied them to cloud storage. We were able to stop the VM. VM is no longer running, but the files are still available, and we're able to serve them out. In the demo at the end of the previous section, I copied the ingested and transformed files out of the compute instance into cloud storage. This way, we could stop our compute instance and retain access to the data. While we've discussed the demand for a great amount of computing power for today's big data and ML jobs, we still need a place to store all the data that's generated. As with the demo, this needs to be separate from the compute instances so that we can analyze it, transform it, and feed it into our models. This is one major way that cloud computing differs from desktop computing. Compute and storage are independent. You don't want to think of disks attached to the compute instance as the limit of how much data you can process and store. Getting your data into your solution and transforming it for your purposes should be your first priority. In the roles and team structure discussions that I'll talk about later in this module, I'll talk about the need for data engineers to build data pipelines before you can start building machine learning models from that data. And when the pipeline is built, the job isn't done. Because once the data is in your system, data engineers are still needed to replicate the data, back it up, scale it, remove it as needed, all at scale. Instead of data engineers managing storage infrastructures themselves, data engineers can use Google Cloud Storage, which is a durable global file system. Creating an elastic storage bucket is as simple as using the web UI in console.cloud.google.com or the Google Storage Utility function called gsutil in the command line interface. As an additional level of flexibility, a data engineer can choose what type of storage class they want for their data.
There are 4 storage classes for you to choose from based on your data needs: standard storage, nearline storage, cold line storage, and archive storage. Regardless of which one you choose, all classes have multi-region, dual region, and region location options. So they differ based on the access speed and the cost. Standard storage is the fastest, and archive storage is the least expensive. A good trade-off, for example, is to use nearline storage for data that you might access only monthly. For data analysis workloads, it's common to use a standard storage bucket within a region for staging your data. Why do I say within a region? That's because you need the data to be available to your data processing computing resources. And these will often be within a single region. Co-locating your resources this way maximizes the performance for data-intensive computations and can reduce network charges. Cloud storage buckets are an example of a cloud resource. Let's cover some of the account management logistics that you need in order to use cloud resources.
Starting from the most granular objects, you see that resources, like your cloud storage bucket or compute engine instance, these resources belong to specific projects. Bucket names have to be globally unique, and GCP assigns you a project ID that's globally unique too. And so you can use that project ID as a unique name for your bucket. But what's a project? A project is a base level organizing entity for creating and using resources and services, for managing billing, APIs, and permissions. Zones and regions physically organize the GCP resources you use, whereas projects logically organize them. Projects can be created, managed, deleted, even recovered from accidental deletions. Folders are another logical grouping you can have for collections of projects. Having an organization is required to use folders. But what's an organization? The organization is a root node of the entire GCP hierarchy. While it's not required, an organization is quite useful because it allows you to set policies that apply throughout your enterprise to all the projects and all the folders that are created in your enterprise. Cloud Identity and Access Management, also called IAM or IAM, lets you fine-tune access control to all the GCP resources you use. You define IAM policies that control user access to resources. Remember, if you want to use folders, you must have an organization. Now that you have a Google Cloud Storage bucket created, how do you get your data on the cloud and work with the data once it's there in the bucket? In the demo, I used gsutil commands. Specifically, we can use cp for copy and specify a target bucket location. If you spin up a Compute Engine instance, the command line tool gsutil is already available and we can do gsutil copy. On your laptop, you can download the Google Cloud SDK so that you can get gsutil. gsutil uses a familiar Unix command line syntax. So if you know how to use the cp command on Unix, you know how to use gsutil cp. So far, we've looked at compute and we've looked at storage. The third part of Google Cloud infrastructure is networking. Google's high-quality private network, petabit bisectional bandwidth, and edge points of presence are combined using state-of-the-art software-defined networking to deliver a powerful solution. First, the private network. Google has laid thousands of miles of fiber optic cable that crosses oceans with repeaters to amplify optical signals. And as you can see in this amusing GIF, it's shark-proof. Google's data centers around the world are interconnected by this private Google network, which by some publicly available estimates carries as much as 40% of the world's internet traffic every day. This is the largest network of its kind on Earth, and it continues to grow. Second, the petabit bisectional bandwidth. One of the themes we will discuss in this course is a separation of compute and storage. You no longer need to do everything on a single machine or even a single cluster of machines with their own dedicated storage. Why? Well, if you have a fast enough network, you can perform computations on data located elsewhere, like many distributed servers. Google's Jupyter network can deliver enough bandwidth to allow 100,000 machines to communicate amongst each other. So for any machine to communicate with any other machine in the data center at over 10 gigabits per second. This full duplex bandwidth means that locality within the cluster is not important. If every machine can talk to every other machine at 10 Gbps, racks don't matter for data analytics and machine learning. But you need to ingest data, probably from around the world. You need to serve out the results of your analytics and predictions, perhaps to users who are all around the world. This is where edge points of presence come in. The network, Google's network, interconnects with the public internet at more than 90 internet exchanges and more than 100 points of presence worldwide. When an internet user sends traffic to a Google resource, Google responds to the user's request from an edge network location that will provide the lowest delay or latency. Google's edge caching network places content close to end users to minimize latency. Your applications in GCP, like your machine learning models, can take advantage of this edge network too. The last piece of core infrastructure underpinning your data pipelines and machine learning models is Google-grade security. When you build an application on your on-premises infrastructure, you're responsible for the entire stack's security, from the physical security of the hardware and the premises in which they are housed, through the encryption of the data on disk, the integrity of your network, and all the way up to securing the content stored in those applications. But when you move an application to GCP, Google handles many of the lower layers of security, like the physical security of the hardware and its premises, the encryption of data on disk, and the integrity of the physical network. Because of its scale, Google can deliver a higher level of security at these layers than most customers could afford to on their own. The upper layers of the security stack, including the securing of data, remain your responsibility. But even here, Google provides tools like Cloud IAM to help you implement the policies that you define at these layers. Communications over the internet to our public cloud services are encrypted in transit. Google's network and infrastructure have multiple layers of protection to defend our customers against denial of service attacks. Stored data is automatically encrypted at rest and distributed for availability and reliability. This helps guard against unauthorized access and service interruptions. One specific product I'll highlight here that you will see a lot of in this course is BigQuery, Google Cloud's petabyte-scale analytics data warehouse. Data in a BigQuery table is encrypted using a data encryption key. Then, those data encryption keys are themselves encrypted with key encryption keys. This is known as envelope encryption, and it provides additional security. BigQuery also allows you to provide your own encryption keys. These are called customer-managed encryption keys. Inside BigQuery, you can monitor your team's BigQuery usage and running queries and proactively limit access to data at a row and a column level. We'll cover BigQuery as a service in greater detail later. But in this section, we just wanted to point out BigQuery's security controls as an example of the kind of security controls that you will find in every service on GCP. So far, we've talked about low-level infrastructure, compute, storage, networking, and security. However, as a data engineer or data scientist or data analyst, you will typically work with higher-level products. So let's talk about the big data and machine learning products that form Google Cloud Platform. We'll talk about the chronology of innovation, not for history's sake, but so that you understand the evolution of data processing frameworks. Knowing how these frameworks have evolved can help you understand the typical problems that arise and how they're addressed. One of the interesting things about Google is that historically, we have faced issues related to large data sets, fast-changing data, and varied data, what is commonly called big data, earlier than the rest of the industry. Having to index the World Wide Web will do that. And so, as the internet grew, Google invented new data processing methods. In 2002, Google created GFS, or the Google File System, to handle sharding and storing petabytes of data at scale. GFS is a foundation for cloud storage and also for what would become BigQuery managed storage. One of Google's next challenges was to figure out how to index the exploding volume of content on the web. To solve this, in 2004, Google invented a new style of data processing known as MapReduce to manage large-scale data processing across large clusters of commodity servers. MapReduce programs are automatically parallelized and executed on a large cluster of these commodity machines. A year after Google published a white paper describing the MapReduce framework, Doug Cutting and Mike Caffarella created Apache Hadoop. Hadoop has moved far beyond its beginnings in web indexing and is now used in many industries for huge varieties of tasks that all share the common theme of volume, velocity, and variety of structured and unstructured data. As Google's needs grew, we faced the problem of recording and retrieving millions of streaming user actions with high throughput. That became Cloud Bigtable, which was an inspiration behind HBase or MongoDB. One issue with MapReduce is that developers have to write code to manage all of the infrastructure of commodity servers. Developers couldn't just focus on their application logic. So, between 2008 and 2010, Google started to move away from MapReduce to process and query large datasets. And instead, they started moving towards new tools like Dremel. Dremel took a new approach to big data processing, where Dremel breaks data into small chunks called shards and compresses them into a columnar format across distributed storage. It then uses a query optimizer to farm out tasks between the many shards of data and the Google data centers full of commodity hardware to process the query in parallel and deliver the results. The big leap forward here was that the service auto-manages data imbalances and communications between workers and auto-scales to meet different query demands. And as you will soon see, Dremel became the query engine behind BigQuery. Google continued to innovate to solve its big data and ML challenges and created Colossus as a next-generation distributed data store, Spanner as a planet-scale relational database, Flume and Millwheel for data pipelines, PubSub for messaging, TensorFlow for machine learning, plus the specialized TPU hardware we saw earlier and AutoML that's going to come later. The good news for you is that Google has opened up these innovations as products and services for you to leverage as part of the Google Cloud Platform. You will practice working with these products in your labs as part of this fundamentals course.
Hello and welcome. I'm Philip Meyer, a course developer with Google Cloud Platform, and this is a brief tutorial on using QuickLabs in this course. You're about to use the interactive hands-on labs platform called QuickLabs, which is part of Google Cloud. QuickLabs allows you to get practical hands-on experience with GCP and provisions you with Google Account credentials so you can access the GCP console at no cost. Once you reach the lab item in this course, click the Open button. You will then be prompted to provide the email that you want to use for your QuickLabs account. If you already have a QuickLabs account, you can use that email and then log in with your QuickLabs password. If you don't have a QuickLabs account, a new one will be created for you with the email that you provide. Once you're in QuickLabs, click the Start Lab button and wait until lab running is displayed. For each lab, you will have a timer with the remaining access time. You can see that right up here, and your lab will automatically end when the timer runs out. To get started, you want to click the Open Google Console button, and you're going to want to sign in with the username and password that are provided in this pane over here. So let me copy the username, click Open Google Console. I'm going to paste in that username. I'm going to go back and grab the password. I'm going to paste that in as well. And Qwiklabs creates a new account for you each time you launch a lab. Therefore, you're going to have to click through some initial account setup windows. So in this case, I'm going to accept this over here. I don't need to do anything here. I can just click Done. And then once I'm in the GCP console, I can verify that I'm using the Qwiklabs provided account and project. I first need to also agree to the terms of service. I click Agree and Continue. And then over here within the dashboard, I can see the project name, the project ID, the project number. I can also see the project ID up here. And I want to make sure that these are the same and that they match the connection details that we have in the Qwiklabs page. So let me go and verify that this here corresponds to the project ID over here. And we can see it's just cut off slightly there. There we go. So indeed, we are using the right project. And we can also verify that we're using the right username. You can click on this icon up here. We can see we're not logged in with our own account, but with the Qwiklabs provided account. And this is very crucial. So let's also verify that this corresponds to the username that we are provided over here. Okay. Now, some labs track your work within the Qwiklabs provided GCP projects. And if this is enabled, you'll see a score in the top right corner of the Qwiklabs window, as you can see right here. And your score increases as each of these objectives here are met. And you can click on the score to view, as you can see here, the individual steps. So let me go ahead and complete these activities to show you what that looks like. Now that I have completed the lab, I can see that my score has been updated and I'm ready to click End Lab. And once I click End Lab and confirm so, the Qwiklabs provided project and any resources within that project will be deleted, and I can continue learning in Pluralsight. That's it for this tutorial. Remember to use the Qwiklabs provided credentials to sign into the GCP console. Good luck with the labs and enjoy the rest of this course.
choosing which big data and machine learning products are the right mix for your solution is a critical skill that you have to learn. Later on in this module, you will get the opportunity to examine the architecture that real Google Cloud customers use so that they can serve as inspiration. Let's review the options available to you for compute and storage services so that you can better interpret those use cases later. The service that might be the most familiar to newcomers is Compute Engine, which lets you run virtual machines on demand in the cloud. It's Google Cloud's Infrastructure as a Service, or IaaS, solution. It provides maximum flexibility for people who prefer to manage server instances themselves. GKE, Google Kubernetes Engine, is different. Where Compute Engine is about individual machines running native code, GKE is about clusters of machines running containers. Containers have code packaged up with all its dependencies. So GKE enables you to run containerized applications in a cloud environment that Google manages for you under your administrative control. Containerization is a way to package code that's designed to be highly portable and to use resources very efficiently. Since most use cases involve multiple programs that need to execute and communicate with each other, you need a way to orchestrate the containers running these separate programs. That's what Kubernetes does. Kubernetes is a way to orchestrate code that's running in containers. Although Kubernetes and GKE are outside the scope of this course, I'll link to our cloud architecture specializations in the course resources. App Engine is GCP's fully managed Platform as a Service, or PaaS, framework. That means it's a way to run code in the cloud without having to worry about infrastructure. You just focus on your code and let Google deal with all the provisioning and resource management. You can learn a lot more about App Engine in the specialization Developing Applications in Google Cloud Platform. Cloud Functions is a completely serverless execution environment, or Functions as a Service, FaaS. It executes your code in response to events, whether those events occur once a day or many times a second. Google scales resources as required, but you only pay for the service while your code runs. So what's the difference between App Engine and Cloud Functions? Typically, App Engine is used for long-lived web applications that can auto-scale to millions to billions of users. Cloud Functions are used for code that's triggered by an event, such as a new file hitting cloud storage. The fastest way to lift and shift your data workloads is by provisioning a VM and running your code. You'll experiment with this later on when you run Spark ML jobs on Cloud Dataproc, which spins up Compute Engine instances for your cluster. Most applications need a database of some kind. If you've built a cloud application, you can install and run your own database for it on a virtual machine in Compute Engine. You simply start up the virtual machine, install your database engine, and set it up, just like in your data center. Alternatively, you can use Google's fully managed database and storage services. What all these, Bigtable, Cloud Storage, Cloud SQL, Spanner, Data Store, what all these have in common is that they reduce the work it takes to store different kinds of data. GCP offers relational and non-relational databases and worldwide object storage. You will learn more about these later on in this course. GCP also offers fully managed big data and machine learning services. Just as with storage and database services, you could build and implement these services yourself, but why manage the infrastructure for compute and storage when it can be fully managed by Google Cloud? Here's a complete list of big data and ML products organized by where you would likely find them in a typical data processing workload. On the left, you will see the foundation to where your raw data is stored. If your data isn't stored on GCP yet, you can ingest it using the tools that you see next. After your data is on GCP, you can analyze it using the tools in the third column and run machine learning on it with the tools in the fourth column. The last column is how you can serve out your data and ML insights out to your users. Now it's time to explore some cool big data and machine learning solutions that have been built using Google Cloud. Then you will get a chance to find a use case and explore it in your own activity. Keller Williams is a US real estate company. Keller Williams uses AutoML Vision to automatically recognize specific features of houses, like this house has a built-in bookcase. This helps agents get houses listed faster and buyers find houses that meet their needs. Neil Dolakia, Chief Product Officer of Keller Williams, says that by training a custom machine learning model to recognize common elements of furnishings and architecture, customers can automatically search home listing photos for specific features like granite countertops, or even more general styles like show me modern houses. This application of machine learning allows Keller Williams realtors to quickly walk around a home and record a video and use the object detection capabilities of AutoML Vision to find and tag key aspects of the home that customers might want to search on. A big benefit for their organization is that they already had many existing images and videos of home walkthroughs already. They simply fed them into the pre-built AutoML Vision model and customized it, all without writing a line of code. You will learn more about AutoML Vision and practice creating machine learning models with it later in this course. Ocado, the UK online-only grocery supermarket, used machine learning to automatically route emails to the department that needed to actually handle them. This avoids multiple rounds of reading and triaging those emails. With their old process, all the mails went to a central mailbox where the email was read and then routed to the person or department that could handle it. Unfortunately, the central mailbox with somebody reading all the emails, that doesn't scale. And so it led to long delays and poor user experience. So Ocado used machine learning, specifically the ability to read an email, to process natural language, to discover customer sentiment and what the message was about so that they could route it immediately and automatically. One last use case. Kewpie manufactures baby food. In this case, quality is not necessarily a matter of safety because the food itself is safe. But if baby food is discolored, it tends to get parents very concerned. So Kewpie turned to Google and our partner BrainPad to build a solution that leverages image recognition to detect low quality or discolored potato cubes. The machine learning algorithm enabled them to free people up from the tiring work of inspection and focused on other more important work. Now it's your turn. One of the best ways to inspire and drive your team and projects to the cloud is to show your stakeholders examples from your industry, examples where someone has already succeeded with building a solution. For this activity, navigate to cloud.google.com/customers and scroll down. For products and solutions, filter on big data analytics and also on machine learning. Select a customer use case that interests you. Then answer these 3 questions. Number 1, what were the barriers or challenges the customer faced? The challenges are important. You want to understand what they were. Second, how were these challenges solved with a cloud solution? What products did they use? And 3, what was the business impact? Take a moment to complete the activity and then return to the video. For our example, we chose Gojek because they use a data engineering solution that maps nicely to the topics that we're going to cover as part of this course. Gojek is an Indonesia-based company that gives shared motorcycle rides, brings goods, and provides a wide variety of other services for over 2 million families across 50 cities in Indonesia. Their app has over 77 million downloads, and they're connected with over 150,000 merchants who sell through their delivery platform. And if you're interested in GIS data, they have over 1 million drivers delivering goods and giving rides across 50 cities, and Gojek gets sensor data from all of these drivers. So Gojek manages more than 5 terabytes per day of data for analysis. The Chief Technology Officer, the CTO, Ajay Gore, gives this meaningful statistic. For example, we ping every one of our drivers every 10 seconds, which means 6 million pings per minute and 8 billion pings per day. That's Gore who's saying this. If you look at the scale and number of our customer interactions as well, we generate about 4 terabytes to 5 terabytes of data every day. We need to leverage this data to tell our drivers where demand from customers is strongest and how to get there. With the success of their on-demand motorcycle ride service, Gojek faced the challenges when looking to scale their existing big data platform. What challenges? Their management team stated, most of the reports are produced 1 day later, so we couldn't identify the problems that were happening as soon as possible. Gojek chose Google Cloud Platform and migrated the data pipelines to GCP so that they could get high performance with minimal day-to-day maintenance. Their data engineering team uses Cloud Dataflow for stream data processing and Google BigQuery for real-time business insights. Their end-to-end architecture looks like this. First, they ingest data from their mobile app, online, and IoT devices on vehicles, like the GPS tracking for deliveries. They ingest this data into Cloud PubSub. Then, the data is brought into Cloud Dataflow for processing, and a variety of other data sources are used to enrich this event data. Finally, after Dataflow has done the processing, Dataflow streams the data into BigQuery, and BigQuery in this case is used as a data warehouse to store the data. What's the business impact? So here's an example of one of the problems that the Gojek team solved. The question was, how could they quickly know which locations had too many drivers or too few drivers? Too few drivers to meet the demand for that area. To solve this problem, what does the team need to do? Number one, they needed to check the demand of bookings by customer against the supply of drivers and do this thing in real time. Then the team needed to identify who these drivers are and notify them to reroute to higher demand areas. How they achieved this was by building a streaming event data pipeline using Cloud Dataflow. Driver locations would ping out to PubSub every 30 seconds, and these locations would go into Dataflow for processing. The Dataflow pipeline aggregates the supply pings from the drivers against the request for bookings and then connects to Gojek's notification system to alert drivers. From a technology standpoint, the system needs to handle an arbitrarily high throughput of messages and scale up and down to process. Cloud Dataflow automatically manages a number of workers processing the pipeline to meet demand. The Gojek team is then able to visualize and highlight supply-demand mismatch areas for management reporting, as you see in this example here. The green dots, the small green dots, represent riders and new booking requests. And the red dots, the small red dots, those are the drivers. So you have the riders in the green dots and the drivers in the small red dots. And then you see the areas that the system has identified as the highest mismatches of supply and demand. Those areas are highlighted in red, like the train station, which has many booking requests, but not enough drivers. The team can now actively monitor and ensure that they're sending drivers to the areas in highest demand, which means faster booking times for riders and more fares for the drivers. So far, you've seen the infrastructure, the software, and the customers who are already using GCP. But the most critical factor to the success of your future big data and ML projects is your team itself. The people and the core skill sets required will make or break your next innovation. A common mistake that companies make is that they go out and hire 10 PhD machine learning scientists and expect magic to happen. I see this a lot with companies who are new to building data science and ML teams. They focus on the ML researchers and forget about all the help and guidance that the ML researchers will need. The reality, as my colleague Cassie has noted in a blog post, looks more like this. You need data engineers to build the pipelines and get you clean data, decision makers to decide how deep you want to invest in a data-driven opportunity while weighing the benefits for the organization, analysts to explore the data for insights and potential relationships that could be useful as features in a machine learning model, statisticians to help make your data-inspired decisions become true data-driven decisions with their added rigor, applied machine learning engineers who have real-world experience building production machine learning models from the latest and best information and research by the researchers, data scientists who have the mastery over analysis, statistics, and machine learning, analytics managers to lead the team, social scientists and ethicists to ensure that the quantitative impact is there for your project and it's the right thing to do. As I've written in a blog post on the subject, it's linked below, a single person might have a combination of these roles, but this depends on the size of your organization. Your team size is one of the biggest drivers in whether you should hire for a specific skill set, upskill from within, or combine the two. Do you remember these big data challenges? Can you see how different roles would map to these? Within Google Cloud Training, my team and I have thought about the different types of data science teams and roles that are using Google Cloud so that we can best tailor our data and ML courses and labs. One of the core challenges we face is how different types of users engage with our GCP big data and AI products. We'll be using a few personas in this course. Their backgrounds, goals, and challenges might be similar to yours. Let's meet them now, and you'll see them again later. Brittany and Theo lead their data engineering team in managing their Hadoop cluster for the organization's data pipelines and compute jobs. Their organization was an early adopter of Hadoop for distributed computing back in 2007, and they've built up Hadoop jobs over time. And Brittany and Theo's job is to actively ensure that the Hadoop jobs are all run and that the cluster is well maintained. They say, our CTO has challenged our data engineering team to find ways we can spend less on managing our on-prem cluster. Right now, we just want to show her options that don't require any code changes to our 100 plus Hadoop jobs. Brittany and Theo are data engineers who manage your company's data platform and are focused on reducing maintenance burden. Jacob is a data analyst who has a background in building and querying his company's MySQL transactional and reporting database. As the company grows, the reporting tables in his RDBMS are already starting to slow down, and users are reporting long query and dashboard loading times. He wants to find an easy path for scaling his company's data reporting and not have to manage another data system as the data needs grow. Jacob is a data analyst who wants to be able to derive insights from data and disseminate them with as little friction as possible. Rebecca is a data engineer whose company specializes in harnessing data from the Internet of Things or IoT devices. She says, I really want to design our data pipelines for the future. For us, that means lots and lots of streaming data from our IoT devices with low latency. Her team lead has asked her to come up with a plan to handle the expected 10x growth in streaming data volumes this year. She wants to future-proof her team's pipelines, but doesn't want to spend hours manually scaling hardware up and down as streaming volume changes. Additionally, her business stakeholder team wants insights from all the IoT devices in the field on their dashboards with minimal delay. Vishal says, I pitched my team on the value machine learning can add, and I've got buy-in to build a prototype. But now I've got to build a prototype. What are some of the easiest ways I can see whether machine learning is feasible for my data? Vishal is an applied machine learning engineer who has a background in building machine learning models in TensorFlow and Keras. His team is growing rapidly, and he's often asked by his leadership to assess the feasibility of machine learning for a wide variety of projects. He doesn't have the time to train and test all of the ideas with custom models, and he wants to empower his data analyst and data engineering teams by teaching them machine learning. Do these personas sound familiar to your role and your team? Next, we learn more about the Google Cloud Platform, big data and machine learning approaches and solutions so that we can address each of these challenges. Hi, I'm Lak. Welcome to the third module of our Big Data and Machine Learning Fundamentals course. This module is on performing product recommendations using Cloud SQL and Apache Spark. We'll cover product recommendations, which is probably the most common machine learning problem employed by businesses. Along the way, we'll also get to look at two Google Cloud products, Cloud SQL, which is a managed relational database, and Cloud Dataproc, which is a managed environment on which you can run Apache Spark. Managed? What's managed? Stick around. We'll start out talking about recommendation systems, what they are, what business applications they power, and consider a typical scenario. In this case, that is product recommendations using machine learning for recommending rental houses. Let's say that our data science team is familiar with Hadoop and Spark, and they've already built a recommendation system. Our mission, which we have chosen to accept, is to migrate this existing recommendation system that our team has built from on-premises cluster to the cloud. We'll look at how you would go about migrating on-premises applications to Google Cloud Platform. In particular, why you would want to migrate an on-premise application to Google Cloud Platform. Maybe it is to avoid the challenges that are associated with utilizing and tuning on-premise clusters. But also, when you move an on-premise application to Google Cloud, you're also moving from dedicated storage to off-cluster storage with Google Cloud Storage. And we'll talk about why that is. Let's start with where you find recommendation systems adding value to businesses. Where have you seen recommendation systems before? One common place that comes to mind is e-commerce product recommendations. A model learns what you like and don't like, what you buy and don't buy, and then starts to suggest similar products that you may not have discovered by yourself. You can then help inform the model explicitly by starring, upvoting, or downvoting your own personal rating of an item, or maybe by adding the item to the shopping cart. Notice how I said explicitly. A model can learn from your preferences implicitly too. Can you think of a few data points that an e-commerce model could learn without you explicitly rating items? Perhaps time spent on the website of particular products. Maybe items that you have last viewed. Maybe where you navigated from, what device you are on, and if you've allowed it, geographic personalization as well. Things that people who live in your neighborhood or your country tend to buy. You have probably seen recommendation engines in Netflix, Amazon, and so on. It's also what Facebook uses to put posts on your newsfeed and what Google uses to personalize your search results. Product recommendations are the first machine learning application that the public recognizes. As in, how does Netflix know that I will like this movie? The general population was pretty unaware of machine learning applications like medical diagnosis, or airline fares, or detecting illegal logging, or playing chess, until it got to product recommendations, where if you like X, you will also like Y. And that tuned the public in to the idea of machine learning. One cool example of a recommendation system is Smart Reply in Gmail. This is the machine learning model that recommends 3 possible answers to your emails. Another is how Google Photos recommends similar photos or groups of similar photos so that you can add them into an album and you can order a printed version of it. Another example is how Google Maps now serves personalized restaurant recommendations. When you explore a new area, the app provides users with a For You tab, which lists restaurants and venues that it thinks you will enjoy based on your history. For example, here you can see that Good Barbecue is a 95% match for me, as well as a recommendation for a new bistro that is trending. A core aspect of a recommendation system is that you need to train and serve it at scale. Think of the machine learning system that drives YouTube recommendations for users. It identifies things that a user may like based on what they've watched in the past and serves them these video recommendations, like these video recommendations that I got when I logged into YouTube. Most of the recommendations here are about programming, TensorFlow, or machine learning, which I guess says a lot about the videos that I like. These recommendations are relevant and useful to me. In the following lessons, you'll implement your own recommendation system for housing rentals. Now that you've seen how recommendation systems are used at Google and in other businesses, it's time to look into the specific scenario that we'll use in the next lab. The core pieces of a recommendation system are data, the model, and infrastructure to train and serve recommendations to users. Our data set for this scenario will be housing rentals that we want to recommend to our users based on their preferences. We'll use a machine learning model to make these recommendations. A core tenet of machine learning is to let the model learn for itself what the relationship is between the data that you have, like user preferences and housing features, and the data that you don't have, like a user's rating on a property that they haven't yet seen. What would this user rate this property if we showed it to them? You will not be writing custom logic like, if the house is a beach house and the season is summer and the user likes cozy houses, then house number 22 is what we recommend. Can you think of the issues if we used such logic instead of letting the model figure it out? What if there were many different kinds of beach houses with all kinds of different features, like the number of bedrooms, locations, amenities? You get the picture. What if you have different kinds of users? Some users who like to go to beach houses in summer and others who like the shoulder season. Hard coding logic for all these features and different kinds of user segments isn't scalable, and it assumes that we always know the right answer for every scenario. Let's illustrate this point with an example. Take Google search. Say you go to Google and search for giants. What should we show you as the results to make it most relevant for you? If you're in California, should we show results for the San Francisco baseball team and the local games nearby? What about if you're based in New York? Should we tailor the results to show the New York Giants football team instead? And should we write this as a rule? Well, up until a few years ago, this is exactly how Google search worked. There were tons of rules that were part of the search engine code base to decide which sports team to show a user when they search for Giants. If the query is Giants and the user is in the Bay Area, show them results about San Francisco Giants. If the user is in the New York area, show them results about New York Giants. If they're anywhere else, show them results about tall people. Just imagine how many if-then or case statements this would be and how hard it would be to maintain. And this is just for one query. Multiply this by the large variety of queries that people make, where they make them from, what device they're on, and what kinds of interests different people have, and you can imagine how complex the code base would become. The code base starts to get unwieldy because hand-coded rules are really hard to maintain. So this is where machine learning comes into play. Machine learning scales much better because it doesn't require hard-coded rules. It's all automated, learning from data in an automated way. That's what machine learning is. Our data set in this case is that we know historically when people searched for giants and we showed them a bunch of links, which of those links did people click on? Since we know this, we have a data set of a query term and the links that people liked. Why can't we train a machine learning model to basically provide a ranking of these links? And that's exactly what Google itself did internally with a deep learning model called RankBrain. After rolling it out, the quality of our search ranking results improved dramatically, with the signal from RankBrain becoming one of the top 3 for influencing how different link results are ranked. If you're interested, I'll provide a link where you can read more about it. We'll revisit machine learning in greater depth in each of the modules in this course. But for now, just remember that machine learning is this idea that we want to teach the computer using examples, not with rules. Any business application where you have those long switch or case statements or if-then logic manually coded, and you have a history of good labeled data. That is data for which you know a good answer or a bad answer, right? A history of good labeled data. Any such application is a possible application for machine learning. So how would housing recommendations work in our system? First, we need to ingest the ratings of all the houses that have already been done by our users when we showed them specific houses. So we have to go to our inventory of rentals and ingest the ratings for the houses. These ratings could come from explicit ratings. Maybe we showed the user the house in the past and they clicked 4 stars after seeing the house details. Or their ratings could come from implicit ratings. Maybe they spent a lot of time looking at the website corresponding to this property. Then we'll train a machine learning model to predict a user's rating of every house that we currently have in our listing database. We will then pick the top 5 rated houses that they haven't already seen. People who are not aware of recommendation engines somehow think of a car appearing on their Facebook feed because they happen to read an automobile review article. They say, oh, I was reading this review article and then just kept seeing cars in my Facebook feed. That's not the case. Reading the article caused the rating of all cars to go up, and the ratings of other items that are not cars to stay relatively the same. And this caused the highest ranking car to get into the top 5. So there was always a rating for the car. The car was always there, but its rating was simply lower before they read the article in question. So how would we predict a user's rating of a house, particularly if they haven't seen it before? The model is based on 2 things. It's based on your other ratings. What have you rated other houses? And other people's rating of this particular house. A particularly simple model could be to look at all the users who rated this particular house and find the 3 users in that list who are most like you. Maybe they live in your country, maybe they have the same age, maybe they went to the same college. Find the 3 users in that list who are most like you. And then the prediction is the average of those 3 users' ratings. This is not a great model, of course. It's too easy to game. Think about what happens if 3 people gang up together and rate a house that nobody else cares about. So there are only 3 ratings for this house. So the 3 closest users are going to be these 3 people. So for sparse houses, it's really easy to game. But this idea of using user ratings of a particular house and users like you helps convey the basic premise of how recommendation models work. So where is the machine learning here? Where is the learning? The model would have to figure out how to find the users who are most like you. How many users to consider? 3 users, 5 users, 7 users, how many? And how to weight the different factors, such as the overall popularity of the items you have in common, and so on. This can be done by seeing what parameters help predict if you intentionally withheld ratings best. So we may have thousands of items and only 2 to 3 reviews per item. The chances are those reviewers have nothing in common with the user that we want the rating for. So, because this rating matrix is extremely sparse, we need to cluster items and users together. To put this in a more intuitive way, imagine that all of your friends drive SUVs, sport utility vehicles, and you read an article on Porsche. The car that appears on your feed might be a Porsche SUV, even if the article was on Porsche cars and all your friends drive Toyota SUVs. The machine learning model is imputing a rating for a Porsche SUV that is quite high, even though none of your friends rated it. So the machine learning model is essentially asking, who is this user like? And secondly, is this objectively a house that people tend to rate highly? The predicted rating is a combination of both these factors. All things considered, the rating of a house for a particular user will be the average of the ratings of users like this user, but it's calibrated by the quality of the item itself. Now that we understand the problem and the approach, we need to address the last question, the infrastructure question. How often and where will you compute the predicted ratings? And once you have them, once you've computed these ratings, where would you store them? What do you think? How often and where will you compute the predicted ratings? It's not as if rental recommendations have to be updated every time some user somewhere rates a house. We don't need to update the rental recommendations every time a new rating appears in our system. It's probably sufficient if we update the recommended houses for users once a day, maybe even once a week. In other words, this does not need to be streaming. It could be batch. On the other hand, we will probably have thousands of houses and millions of users. So it's probably best that we compute the rating that every user will give every house. We do that computation in a scalable way. We don't want to do it on a single machine. We want to do it in a fault-tolerant way that can scale to large data sets. So a typical solution for computation that has to happen over large data sets in a fault-tolerant way is to do it in a big data platform like Apache Hadoop. Finally, where will you store the computed ratings? Why would you want to store them? Well, we probably want to power a web application with these recommendations, and we don't want to compute recommendations when the user visits a web page. We want to pre-compute these recommendations. As we said, it's a batch job. So once a day, once a week, we pre-compute it. And then when the user logs on, we want to show that user the recommendations that we pre-computed specifically for them. So we need a transactional way to store the predictions. Why transactional? So that while the user is reading these predictions, we can update the predictions table as well. Assuming that there are 5 predictions for every user, and we have 1 million users, that's a table of just 5 million rows. It's small enough and compact enough that a typical solution for this would be to store the data in a relational database management system, an RDBMS like MySQL. So we decided to use a big data platform like Hadoop and an RDBMS like MySQL to solve the housing recommendations problem. These are both open source technologies. You probably have Hadoop clusters and MySQL database running on premises. So let's assume that your team already has this recommendation system working on-prem and see how to migrate it from on-premises to Google Cloud Platform. Of course, you want to do that only if the migration can add value. So we will look at that as well. For our housing recommendation model, let's say our data science team already has a working on-premise model using a Spark ML job on your Hadoop cluster. They're interested in the scale and flexibility of GCP, and they want to do a like-for-like migration of their existing Spark ML jobs from on-premises, and they want to do this as a pilot project. As explained in the previous lesson, we can get away with computing predicted ratings once a day. We don't need to compute recommendations in real time. So Hadoop batch processing is enough. Here, we'll use Spark ML, but instead of doing it on premises, we'll run the machine learning job on Cloud Dataproc and store the ratings in an RDBMS in Cloud SQL, because this is a relatively small data set of 5 recommendations for every user. So this is what you will practice in your first lab. Incidentally, this is why the Smart Reply in Gmail is so amazing. Unlike our housing recommendations, Smart Reply's recommendations have to be done in real time when a new email pops up in your mailbox. Needless to say, Gmail is doing something far more sophisticated than what we're talking about here. Here is how we decided on using Cloud SQL among the other big data products available for storing our ratings. This is a good reference to follow based on your storage access pattern. We'll cover the solutions in your other scenarios in this course, but briefly, use cloud storage as a global file system. Use Cloud SQL as an RDBMS, as a relational database management system for transactional relational data that you access through SQL. Use DataStore as a transactional NoSQL object-oriented database. Use Bigtable for high throughput NoSQL append-only data. So not transactions, append-only data. So a typical use case for Bigtable is sensor data for connected devices, for example. Use BigQuery as a SQL data warehouse to power all your analytics needs. So here, we wanted a transactional database, and we expect to have data volumes in the gigabytes or less, and so hence, Cloud SQL. If you're a more visual learner, here is another good map of visualizing where to store your data in GCP. If your data is unstructured, like images or audio, use cloud storage. If your data is structured and you need transactions, use Cloud SQL or Cloud Data Store, depending on whether you want your access pattern to be SQL or NoSQL. And by NoSQL, we mean a key value pair. In other words, you'll be trying to search for data based on a single key, use Data Store. If you'll be finding data using SQL, use Cloud SQL. Cloud SQL generally plateaus out at a few gigabytes. So if you want a transactional database that is horizontally scalable so that you can deal with data larger than a few gigabytes, or if you need multiple databases, so you want them spread globally, use Cloud Spanner. So another way to say it is, if one database is enough, use Cloud SQL. If you need multiple databases, either because you have a lot of data or because your application needs to be transactional across different continents, use Cloud Spanner. If your data is structured and you want analytics, consider either Bigtable or BigQuery. Use Bigtable if you need real-time, high-throughput applications. Use BigQuery if you want analytics over petabyte-scale datasets. For our housing recommendation use case, we want to store our ratings and predictions somewhere. This is a structured dataset of user ratings and houses. It's built for a transactional workload, writes and reads, and one database is enough for a small dataset, and hence we pick Cloud SQL. So what's Cloud SQL? It's a Google-hosted and managed relational database in the cloud. Cloud SQL supports two open source databases, MySQL and Postgres, and other database solutions. In our case, we'll be using MySQL. One of the advantages of Cloud SQL is that it's familiar. Cloud SQL supports most MySQL statements and functions, even stored procedures, triggers, and views. It brings the benefits of cloud economics in the form of flexible pricing. You can pay for what you use. What do I mean by that? GCP manages the MySQL instance for you. This means things like backup and replication. It's on the cloud, so you can connect to it from anywhere. You can assign it a static IP address, and you can use typical SQL connector libraries. Because it's behind the Google firewall, it's fast. You can place your Cloud SQL instance in the same region as your App Engine or Compute Engine applications and get great bandwidth. Also, you get Google security. Cloud SQL resides in secure Google data centers. So that covers where we'll be storing the recommendations. But how will we compute these recommendations in the first place? Where will we be doing the compute? Let's review where big data computations have been done historically and even today. Before 2006, big data meant big databases. Database design came from a time when storage was relatively cheap and processing was expensive, so it made sense to copy the data from its storage location to the processor to perform data processing, and then the result would be copied back to storage. Around 2006, distributed processing of big data became practical with Hadoop. The idea behind Hadoop is to create a cluster of computers and leverage distributed processing. HDFS, the Hadoop Distributed File System, stored the data on machines in the cluster, and MapReduce provided distributed processing of this data. A whole ecosystem of Hadoop-related software grew up around Hadoop, including Hive, Pig, and Spark. Around 2010, BigQuery was released, which was the first of many big data services developed by Google. Around 2015, Google launched Cloud Dataproc, which provides a managed service for creating Hadoop and Spark clusters and managing data processing workloads. The other piece of our system is a software that runs on Hadoop. The software in this case is to train a machine learning model for creating housing recommendations. In this case, we used SparkML, which is part of Apache Spark. Apache Spark is an open source software project that provides a high-performance analytics engine for processing batch and streaming data. Spark can be up to 100 times faster than equivalent Hadoop jobs because it leverages in-memory processing. Spark also provides a couple of abstractions for dealing with data, including what are called RDDs, or resilient distributed datasets and data frames. Okay. We'll be using our Spark job for the housing rental recommendations, but we'll be doing the computation on Cloud Dataproc.
One of the most common use cases is running your Apache Spark jobs on your Hadoop cluster. Now let's do a demo of creating a new cluster and running a Spark job using Cloud Dataproc. And our goal will be to do it in 10 minutes or less, which if you've ever seen an on-premises Hadoop cluster by yourself, that seems like a pretty big win for infrastructure setup time and efficiency. Let's get started. All right, here we are in the Google Cloud Platform console. This is Cloud Dataproc. How you get here is if you open up the navigation menu. I've got several favorites that I've pinned here, but I'll show you how to actually, if you scroll down in the products and services to big data, you see a lot of the products that we mentioned so far. Dataproc is right here. If you click that pin, that'll bring it all the way up here, which saves it, which is a nice little efficiency hack. Hovering over the Cloud Dataproc service, you'll see that you can click on clusters, jobs, or workflows. But if you just click on the logo, that'll take you to the clusters page. So here we have it. It is blank slate. So the first thing we wanted to do is create and provision an Apache Hadoop cluster on Dataproc. So the configuration details, as you might expect, are here. We'll give the cluster a great name. We're going to be estimating the digits of pi in a distributed fashion, so we'll just call it pi cluster. Here you can choose what type of availability, which is essentially the ratio of how many master nodes do you want to your n worker nodes. So we'll keep it standard. If you want to adjust the hardware, which is your compute, your CPUs, you can do that here. All the way down to, at the time of recording, having 160 virtual CPUs in ultra memory. We're going to keep just the standard here. And 15 gigabytes of memory, 500 gigabytes of persistent disk, sure. These are all the settings. So if you're running a pilot project, for an apples to apples comparison, just map your same infrastructure that you're using for your clusters. And the number of nodes we're going to maintain at just the 2 is there. And we'll go ahead and click create. While that cluster is spinning up behind the scenes, we'll go ahead and just fill out a job to start with. So I already ran a job previously, and you can tell that since I didn't have a cluster before, that I actually turned down that cluster. So we're going to be creating a brand new job. So click on submit job. You can keep the job ID, or we'll just call this estimate pi digits. Region global is fine. It's good that we have the cluster name, even though it's spinning up. It still has it here. You can submit a job and queue it to run. Job type, it's not a Hadoop job, it is a Spark job. You can see the different job types that you could select here. And now we need to find the Java class. This is SparkPy. I'll link the example, but you can actually see there's a bunch of other Spark examples that you can run. And it essentially just, it generates a ton of pairs of XY coordinates on a unit circle, or a circle with a diameter of 1, inside of a square, which is the Monte Carlo method for estimating the number of digits in pi. If you're interested, I'll link that there, but it's essentially we're running that and using the Hadoop worker nodes to process that in massive parallel. And the actual example where the jar file is, I'll just paste that in there from the example, And we are going to generate 1,000 of those XY pairs. That's just an argument that we're passing through. This is specific to the job that we're running. Don't always put 1,000 for the arguments unless your program requires it. And we'll go ahead and submit it. Now it's going to run. Let's see if that cluster is ready for use. Yes, we have the green check mark here. If we wanted to, you can actually click into the cluster and get a lot of really good monitoring metrics that you see here. From within there, you can see the jobs that are running. In this case, for the last 30 seconds, we've had this estimate pi digits job. Let's go ahead and monitor that job specifically. Naturally, you can have multiple jobs running on a cluster, multiple clusters running multiple jobs, and boom, we get the output of our job. We see that it started here, and if we scroll down far enough, it should give us a logged output. Boom, here we go. Where it actually submitted the application, and we get the result, which is the pi estimation right here, and then the job is complete. Spark has been stopped. So now what you can do is we've got a successful job execution. It took 36 seconds, plus the time to spin up the cluster. Is the real power is you can go ahead and turn down that cluster now. Now, if you wanted to have a long-lived cluster because you had persistent data on there, sure, absolutely. We'll be talking a little bit about later about the separation of compute and storage to try to get out of using persistent disks on clusters and into using something like Google Cloud Storage. But if we don't need this cluster anymore, we're not trying to persist any data. We have already ran our calculation. It's just as simple as clicking the delete icon and bring that cluster down. Don't worry about managing the infrastructure. You've got what you needed from that particular job. Or if your job's done, you want to submit more jobs or rerun the same job here. Use however many clusters, whatever size of clusters, edit the resources on the fly. The big takeaway is that clusters are now what we call fungible resources. They're ephemeral. You use them when you need them to submit your jobs. If you need them longer, or if you need them shorter, if you need more clusters or fewer clusters, you can manage that infrastructure automatically here through Cloud Data Proc. That's in essence what it is. So my challenge to you is inside of your lab a little bit later when you're building the recommendation engine using Cloud SQL and Cloud Data Proc, experiment within Cloud Data Proc, take a look at the logs for each of your different running jobs. And if you're running on-premise workloads within Hadoop, see if you can experiment with running some of those jobs within Cloud Data Proc and see which one is more efficient.
We said we would talk about common big data challenges and how they're addressed. One of the most common challenges for managing on-premise Hadoop clusters is making sure they're efficiently utilized and tuned properly for all the workloads that their users throw at them. So let's check in with our team and see what challenges they are facing running the Spark ML job on their on-premise cluster. Our team has an on-premises data center running Hadoop represented by the blue box here. On any given week, they manage 4 different jobs for the organization. Our Spark ML recommendation job is one of the 4. The data is persisted in traditional HDFS disk-based storage. So here's an example scenario that might seem familiar to you. The team launches job number 1. Say for argument, it's a big data pipeline job, which ramps up and consumes 50% of the available on-premises cluster resources. Then, the team has a special request from marketing to run their prediction job for an upcoming campaign later today. That will be job number 2, and it ramps up and consumes the other 50% of available cluster resources. You probably see the problem now. If our Spark ML job was number 3 or number 4, it would get starved out of resources because the cluster's compute capacity is under-provisioned for the demands of the organization's Hadoop jobs. Or a costly alternative is where only one job is running and uses 50% of the cluster resources, and the other 50% of machines are powered and available, but they're not needed. The problem here lies in the static nature of the on-premise cluster capacity. The team needs a better way to optimize the usage of the cluster's resources without the headache of continually tuning and adding and removing servers themselves. This is where GCP can help. You can now think of clusters as flexible resources. With Cloud Dataproc, GCP's managed Hadoop product, you can spin up as many or as few cluster resources as your job needs in the cloud. Notice how I said cluster resources. You use them when you need to run jobs and turn them off when they're not needed anymore. So in this scenario, we can have jobs 1 and 2 run on their customized cluster number 1, and jobs number 3 and number 4 can then run on their own clusters too. Your jobs get the resources that they need. And you can shut down the clusters when they're not in use. The clusters themselves become fungible resources. You can even automate when the cluster shut down, so you don't pay for resources that you're not using. You can set shutdown triggers based on how long a cluster has sat idle, or a specific timestamp, or a duration in seconds to wait, or when you submit a job, run this job and shut down. But what if the needs of a job change, and on some days we need a bigger cluster, and on some days we need a smaller cluster? Cloud Dataproc auto-scaling provides flexible capacity to help you meet that need. It makes scaling decision by looking at Hadoop's yarn metrics. And you can use auto-scaling as long as when you shut down the cluster's node, it doesn't remove any data. So you cannot store the data on the cluster. But that's why we store our data on cloud storage or Bigtable or BigQuery. We store our data off cluster. So auto-scaling works as long as you don't store your data in HDFS. In addition to auto-scaling, another advantage of running Hadoop clusters on GCP is that you can incorporate preemptible virtual machines into your cluster architecture. Preemptible VMs are highly affordable, short-lived compute instances that are suitable for batch jobs and fault-tolerant workloads. Why fault-tolerant? Because preemptible machines, they offer the same machine types and options as regular compute instances, but they last only up to 24 hours, and they can be taken away whenever somebody else comes along and offers up compute needs for them. So if your applications are fault-tolerant, and Hadoop applications are, then preemptible instances can reduce your compute engine costs significantly. How significant? Preemptible VMs are up to 80% cheaper than regular instances. The pricing is fixed. You get an 80% discount. So you always get low cost and financial predictability without taking the risk of gambling on variable market pricing. But just like auto-scaling, preemptible VMs work when your workload can function without the data being stored on the cluster. You want to store the data off cluster, and that's what we will look at next. As you might remember from the demo earlier, separating compute and storage enables cost-effective scale for workloads. With the notion of turning down clusters, you may be worried about all the data that's currently stored on disk HDFS. You may be using HDFS on premises. What happens to that with our new Google Cloud Platform architecture? Your data is not stored in the cluster. Your data is now stored off cluster in Google Cloud Storage buckets. Really? Won't that make things slow to reach out across a network each time the cluster needs some data? Recall that earlier we mentioned Google's data center bandwidth between compute and storage. We talked about a petabit bisectional bandwidth. What that means is that if you draw a line somewhere in the network, the bisectional bandwidth is the rate of communication at which servers on one side of the line can communicate with servers on the other side. With enough bisectional bandwidth, any server can communicate with any other server at full network speeds. With petabit bisectional bandwidth, the communication is so fast that it no longer makes sense to transfer the files and store them locally. Instead, it makes sense to use the data from where it is stored. So here's a plan. We'll use HDFS, but we'll use HDFS only on the cluster for working storage during processing. But we'll store all actual input and output data on Google Cloud Storage. Because the input and output data is off the cluster can be created for a single job or type of workload and can be shut down when not in use. Changing your code that works on-prem to have it work with the data on cloud storage is easy. Just replace HDFS in your Spark or Pig code with GS. So you take the HDFS URLs, HDFS : and replace it with GS : //. This will make the Spark or Pig job read or write to cloud storage. That's it. There's also an HBase connector for Cloud Bigtable. So if you have your data in Bigtable, you can use the HBase connector. And there's a BigQuery connector that you can use to work with data if the data is in the analytics warehouse. So when we say off cluster storage, we're talking about cloud storage, or we're talking about BigQuery, or we're talking about Bigtable. So Cloud Data Proc and Google Cloud Storage are tightly coupled with other GCP products. So storing your data off cluster means that you can process this data not just with Spark from Dataproc, but also from all these other products. Not to mention, storing it off cluster in GCS is generally cheaper since A, disks attached to compute instances are expensive in and of themselves, and B, if your data are off cluster, you get to shut down the compute nodes when you're not using them. So bottom line, store your data in Google Cloud Storage. Friends don't let friends use HDFS. So let's recap what we've covered. You can get a Cloud Dataproc cluster up and running in about 90 seconds. This gives you all of the power of Hadoop without having to manage clusters. As you saw, you can lift and shift your existing Hadoop and Spark workloads by simply replacing HDFS : URLs with GS : URLs. You can connect Cloud Dataproc to Google Cloud Storage and unlock the benefits of both scale and cloud economics. You get to provision a cluster per job if you want to, and shut the cluster down when you're done. Lastly, your clusters are customizable, which could include auto-scaling and preemptible VMs so that you get cost savings. It's now time for your lab. You are in charge of migrating your company's existing machine learning workload for housing recommendations from your on-premises Hadoop cluster to the cloud. Your organization is happy with the current model, but the underlying infrastructure on-premise is causing them headaches to tune and utilize efficiently. Your CTO wants as little friction as possible from your existing Hadoop on-premise infrastructure, but has heard of the advantages that cloud solutions offer for auto-scaling and serverless management. So here are your lab objectives. Create a Cloud SQL instance and populate the tables. explore the rentals data using SQL statements using Cloud Shell, launch Dataproc, train and apply a machine learning model written in PySpark to create product recommendations. Explore the inserted rows in Cloud SQL. Here's what the setup will look like. In step 1, we set up Google Cloud Storage and Cloud SQL, and then import the records from GCS into Cloud SQL. And now that your ratings are in Cloud SQL, in step 2, you will run a machine learning training job in Cloud Dataproc to read those ratings and train the machine learning model. In step 3, you will run the model in Cloud Dataproc to create recommendations and save the top 5 recommendations for each user back into Cloud SQL. Lastly, step 4, your ratings can be delivered back to users through App Engine. You won't do steps 1 and 4 in this lab because those steps deal mostly with web programming. In this lab, you concentrate on doing steps 2 and 3. Try out the lab and keep in mind that you have multiple attempts for each lab, and you can always come back and practice more.
Hi, Evan here, and in this module, we'll explore in great detail some of the cool things that you can do with SQL inside of BigQuery. Now, I know what some of you may be thinking. SQL? Isn't that just used for selecting and returning records from my database? Well, as the title shown here has already probably spoiled it, you can now build machine learning models with SQL too. It's literally my favorite feature in Google Cloud Platform, so I'll spend lots of time walking you through how you can create and analyze the performance of your ML models right within BigQuery where your data lives. But before we jump headlong into ML, we'll first introduce you to BigQuery as a service, which allows you to have a petabyte scale analytics data warehouse. You'll soon learn that BigQuery is actually 2 services in one: a fast SQL query engine and fully managed data storage. Then, we'll show you some of the other cool built-in features, like using GIS functions on your geographic data, and how you can even visualize those insights on maps. Next, we'll expand on our course theme of applying ML to your datasets by looking at how to choose the right model type for your structured data. Lastly, we'll build a custom model using just SQL with BigQuery ML. I'll also show you how I commonly organize my ML projects and some advanced BigQuery ML features that let you do things like see which fields the model thinks are most important in making those predictions. Sound good? Let's get started. BigQuery is designed to be an easy-to-use data warehouse where you can focus on writing SQL statements on small or large datasets without worrying about infrastructure. If you've never written SQL before, I'll also provide resources and labs to get you up to speed as we go. So that's point number one. It's serverless. BigQuery's default pricing model is pay-as-you-go, where you pay for the number of bytes of data that your query processes and any other permanent data that's stored inside of BigQuery. Now, there is some magic built in, like automatic caching of query results, so you don't end up paying for the same query returning the same data twice, which is kind of cool. If you want to have a set bill every month instead, you can subscribe to flat tier pricing, where you get a special reserved amount of resources for your dedicated use. Data in BigQuery is encrypted at rest by default. You can also specify the geographic locality of your data if you need to meet things like regulatory requirements. Controlling access to your data can be as granular as specific columns, say any column tagged with PII, personally identifiable information, or specific rows, like if your marketing team only needs access to see certain rows in one of your tables. BigQuery works in tandem with Cloud IAM to set these roles and permissions at a project level and then inherit it down to the BigQuery level. We'll discuss data access in detail a bit more later. SQL as a language has been around since the 1970s, and just watching the functionality added to the language over time has been awe-inspiring. You can now perform those GIS functions and like distances from lat long points and much, much more. Your data itself, think of your data sets. It most likely has some kind of geographic component, like city, state, zip code, latitude, longitude. So now it's high time to unlock those additional insights. Lastly, BigQuery as both a data warehouse and an advanced query engine is foundational for your AI and ML workloads. It's common for data analysts, engineers, and data scientists to use BigQuery to store, transform, and then feed those large data sets directly into your ML models. This is a huge leap over training ML models on just a few small samples of your data locally on your laptop or desktop. You can now train on all the data that you have available. That's big news for ML. That's the elastic data warehouse nature of BigQuery for ML datasets. Beyond that, as you've seen in the demo, you can now write ML models directly in BigQuery using SQL. This is a great start for model prototyping, as you can quickly engineer what features to use right where your data lives. So what does a typical data warehouse solution architecture look like? Take a look at the green box. BigQuery is the analytics engine that sits at the end of a data pipeline, like Cloud Dataflow. It stores all the incoming data from the left and allows you to do your analysis and your model building. On the far right, you can see the myriad of visualization and other analytical tools that you can connect to BigQuery as a back-end data source. For ML engineers, once your dataset is in BigQuery, you can easily call it from your IPython ML notebooks in the cloud with just a few commands. If you're a business intelligence analyst, you can connect out to visualization tools like Data Studio, Tableau, Looker, QlikView, and more. Lastly, and worth mentioning here, if you have a team of analysts who prefers to work in spreadsheets, you can now query your small or huge BigQuery datasets directly, all of that data directly from Google Sheets, and perform common operations like pivot tables and more on the entirety of your dataset. So no more limitations of rows inside of Sheets. It's a new feature. I'll send a link so you can check it out. But the key takeaway is that BigQuery is a common sink or staging area for your data analytics workloads. Once your data is there, your data analysts, business intelligence developers, and ML engineers can then be granted access to your data to start creating their very own insights.
Let's see if we can execute a large query at scale using BigQuery. In this example, we already have an existing and large BigQuery public dataset for all GitHub repository code that's public, but we'll highlight how you can upload or ingest your own data using the web UI as well. Naturally, you could do this entire demo entirely in the command line or the BigQuery API, but I've got a few surprises that I can show you about the new web UI for BigQuery that you might not have seen before. So here it is. It's our challenge. Let's query over 2.5 billion lines of programming code from GitHub, do it inside of BigQuery, and it'll settle the age-old challenge of whether or not it's more popular for programmers and developers to use tabs or spaces when coding. We'll do that by parsing and processing every single line in over 11 million files, and then group the end report by programming language, like C, Java, Python, or Go, and then interpret the insights. Let's give it a shot. So here we are back in the Google Cloud Platform console. To navigate to BigQuery, this is the web UI. I have it pinned since I commonly use it, but if you scroll down in the products list, you'll be able to find it under Big Data. And you click on BigQuery and that'll take you to the web console. While you're going to be practicing a lot more with the product in the dedicated module on BigQuery, I wanted to show you a quick lightning fast demo of processing a lot of data at scale so you can get inspired to use BigQuery for your own cases. So inside of the console, the majority of the window is taken up by the code editor, which is where you're going to be writing, or in our particular case, pasting an existing script for where we're going to be running lots of analysis on data sets. Now, if your data set doesn't exist, you can create a data set. And once that data set is there, it's an empty bucket where you can create tables. From within there, you can upload data from Google Cloud Storage, you can upload it from a file, link it from Drive, or just create an empty table that you can stream into results later. And that's one of the things that we're going to be doing in our Internet of Things demo a little bit later on. In this particular case, the dataset already exists, and that's going to be the GitHub files dataset. If you wanted to take a look at it after this demo, you can go to Explore Public Datasets. You can type in GitHub. There's lots of public data sets that are available. And you can see it's actually going to be GitHub activity data, which is many, many millions of files that are hosted publicly on GitHub that have been ingested into this public data set for exactly demos and analysis like you see in this demo. So we have an example script that we're going to be running. And the only reason why I made it rather long here is I've broken up each individual part of the code up for our end purpose of looking to see whether or not tabs or spaces is more popular. One of the neat tricks that you can do inside the web UI, if you have a table, in this particular case, you have the project, the BigQuery project, dot, the dataset, dot, the specific table. So it's just collections of collections of collections. You can actually hold down the command or the Windows key, click on that table name, and that'll take you to really useful information about the table, like the schema, what columns are present, how large the table is, and the details. In this particular case, we've just taken a subset, which is about 13 million rows here of the total GitHub data set, and which is 133 or so gigabytes to process. Really useful next step. If you wanted to preview some of the data without running any SQL, you can just click on the preview, and you can see we have individual code files. And if I'll just make this a little bit bigger, you can see the actual code inside of this cell under the content field here. And you can see things like the file path, which we can use to extract the language that the code is written in. Lots of good raw data. And a really good language to process that raw data and analyze it at scale is SQL, or the structured query language. And that's what you see we have written in the script here. So as you might imagine, working through all of this code, we first need to break out the problem at hand. So we know that our code is in there in one large cell. So we break up individual lines using the split function. And essentially it turns that one massive code block into a smaller array. So I'll show you what that actually looks like. You can run just small subsections of code inside of BigQuery by highlighting it and then clicking down on the run arrow and then run selected. So you can see instead of a monolithic block of code, each individual line has now been broken up into that same row of code. Now, the really wild point that you're going to see a little bit later in the BigQuery module, where it's dedicated to topics like this, is it's still technically one row, even though these are broken out in different lines. And the magic there is that BigQuery natively supports arrays as data types, which is cool. So this is just one row with an array of programming lines, however long the program is, stored inside of a new field that we created called line. So it's essentially what the split function does. It says split the content, the blob of the code, by new line into individual lines. Now to actually access, you can imagine what we want to do is look at the first starting character to see if it's a tab or a space to help settle our challenge. We unpack that array using the unnest function that you see there that you'll learn more about. And then we parse out that first character just using a string function, which says, hey, for that flattened line, I want to look at the very first position, the very first character for every single one of those lines of code, and then do a comparison. I've broken up the comparison into this next SQL chunk, which is just using regex to contain whether or not it's a tab, which is that special character there, or if it's the empty space in that first position. Once you've done that, everything from here on out is just aggregating and comparing based on those results to see whether or not tabs are more popular, spaces are more popular. You get the idea. But it showcases you some nice SQL aggregation functions if you're not familiar. There's things like counting the total number of lines, summing the total number of tab instances or instances of spaces, comparing the two with this if operator here. Pretty basic SQL stuff. And then we're extracting out the file path. Remember you saw that .js at the end of that file name? We're just extracting out that here. And then we do a quick filter on an aggregation to make sure that we're excluding the long tail of GitHub code commits and code files that don't ultimately have more than either 10 tabs or 10 spaces. And that helps us kind of trim down to only those real significant programs that have been committed. And then we just do the slight ratio of the sums and a little bit of formatting, and we're good to go. So let me comment back out my little exploration. We'll run this whole thing and process all those millions of lines of code. And what's wild is, since I ran this demo a little bit earlier today, we get the result back immediately because BigQuery behind the scenes can cache queries that says, hey, I've already returned this result, what you can do. And just so I can show you how fast this query will run when it's not caching, because it's a little bit like cheating for the purposes of showing the speed, is we'll actually just run it and say, hey, BigQuery, don't use the cache results. Normally, unless you're trying to show the speed of BigQuery, use the cache. Because if someone is already ran the query against it on your particular project, they can run it again and just get the advantage of that cache query. So you see it took us about 13 seconds, and we processed 133 gigabytes of data from that public data set. So let's expand the rows here and do a little bit of insight diving. So you can see the most popular language by the total number of files, not by the total number of lines. By the total number of lines, it looks like it's C. But total number of files, there's more Java files than there are anything else. We're ordering it by the number of files. And if you wanted to change that for your report, go right ahead. You can do that within the order by in SQL or link it in like a Tableau Looker or Data Studio dashboard. But the real insight is the ratio of tabs to spaces. So just looking quickly down here, you can see spaces are dominate, except in the case of C, which is where tabs have slightly more, 600,000 versus the 500,000 for spaces. Even more interesting insight that you couldn't really get doing this analysis any other way, especially not manually, is the programming language Go actually has the inverse. It's one of the only ones where it has strong tab preference versus space. Now, I'm not a Go expert, but when I did a quick Google search, it's because their compiler, how it actually emits the code, it puts those spaces in for you. It's not like when you're programming in Go, you're doing the spaces consciously instead of the tabs consciously instead of the spaces. So that's BigQuery processing it in 133 gigabytes, 13 seconds with no infrastructure. So you don't need to worry about a lot of the knobs or spinning up clusters to support data workloads, or if multiple queries are running at the same time, is that going to affect your performance? There's a lot that's happening that you don't see. If you're really, really interested, the last thing I'll show you is a really telling stat. So if you click into execution details, and this new web UI that's in beta for BigQuery, you'll see a really interesting stat that I quiz a lot of people on. What do you think slot time consumed means? You know it took 13 seconds to run this query. What is this 49 minutes? If you actually hover over the question mark, it says, it's a unit of computational capacity. So in essence, what BigQuery is telling you, hey, across all of our workers, we did essentially 50 minutes of work massively in parallel, 50 minutes, so that your query could be returned back in 13 seconds. And best of all for you, you don't need to worry about spinning up those workers, moving data in between them, making sure they're sharing all of the results between their aggregations. All you care about is writing the SQL, finding the insights, and then running that query in a very fast turnaround. But there is abstracted from you a lot of distributed parallel processing that's happening. So that is the super high-level BigQuery demo. Later on in the course, you'll see how you can actually write SQL just like this for doing machine learning and exploring those public data sets and building your machine learning model in one of your next labs. We'll see you there. It's time to get a little more technical. So how does BigQuery actually work? Well, it's actually two services in one, as we hinted at earlier. It's both a fast SQL query engine and also a fully managed storage layer for loading and storing your datasets. Keep in mind that it's a serverless service, meaning that's fully managed. Let's take a look at what Google Cloud is managing for you as part of the BigQuery service. The two services are connected by Google's high-speed internal network. Recall that this super fast network enables us to separate compute and storage. So what does each service do? The short answer is that the services are fully managed, so users like you and me don't have to worry about how BigQuery stores data on disk or how it auto-scales machines for large queries. That said, it's a great learning exercise to understand how the services perform their magic so you can better understand what's happening. First up is the BigQuery storage service. The storage service automatically manages the data that you ingest into the platform. Data is contained within a project in what are called datasets, which could have 0 to many tables or views. The tables are stored as highly compressed columns, each column of that table highly compressed in Google's internal Colossus file system, which provides durability and global availability. This is the same data backend that powers some of Google's most popular applications, like Google Photos and Gmail. All the data stored here is only accessible to you and your project team as governed by your access policy, and we'll get into that a little bit more later. The storage service can do both bulk data ingestion and streaming data ingestion, so it'll work with huge amounts of data and also real-time data streams. The query service runs interactive or batch queries that are submitted through the console, the BigQuery web UI, the BQ command line tool, or via the REST API. And the REST API is supported for many common programming languages. There are BigQuery connectors to other services such as Cloud Data Proc and Cloud Data Flow, which simplify creating those complex workflows between BigQuery and other GCP data processing services. The query service runs interactive or batch queries that are submitted through the console, the BigQuery web UI, the BQ command line tool, or via the REST API. And the REST API is supported for many common programming languages. There are BigQuery connectors to other services, such as the one you've seen previously, Cloud Data Proc and Cloud Data Flow, which simplify creating complex workflows between BigQuery and other GCP data processing services. That's why it's called the Google Cloud Platform. Everything is interoperable. The query service can also run query jobs on data contained in other locations. So get this, you can run queries on tables that are a CSV file, for example, that are hosted somewhere else in cloud storage. But before we get too excited about running queries on data that's not in BigQuery, like Google Sheets, you should know that BigQuery is most efficient when it's working off of data contained within its own what's called native BigQuery storage. The storage service and the query service work together to internally organize the data to make your queries run efficiently on terabytes and petabytes. They even optimize your SQL statement syntax wherever possible after you hit that Run Query button. One of the most important controls you have over the resource consumption and costs is controlling the amount of data that your query ultimately processes. In general, You only want to select the columns of data that you actually want to process and return as part of your output. A good rule of thumb is to start broad when you're first exploring the dataset and then zoom in on just those critical fields and rows that you need. Keep in mind, at the time of this recording, BigQuery gives you 1 terabyte of query processing, of bytes processed, at no charge every month, and 10 gigabytes of storage as well to start you off. I'll provide a link to the pricing guide as a reference. In the last lesson, we showed off this SQL statement here, running on the query engine. As any data analyst will tell you, exploring your dataset with SQL is often one of the first steps that you take to uncover those hidden insights. So what is this query actually doing? Care to take a guess? Here, we're counting the total number of trips taken on a public dataset for San Francisco's bike share trips. Now let's explore this public dataset together in greater detail with a quick demonstration. It's now time to dust off your SQL or structured query language skills as we explore some public datasets inside of Google BigQuery. Let's dive right in. So in this demo, how I got to this public BigQuery dataset, which is what we were looking at before, the San Francisco bike share trips, is from this publicly available dataset, BigQuery public data. Now, if you might not have that inside of your QuickLabs account or your own personal accounts, how you can get those datasets is by clicking Add Data, Explore Public Datasets, choosing one of those, and it brings you right back into the console. So I'm going to show you a couple nifty things that I've picked up inside of BigQuery over the years. So now we have a ton of BigQuery public datasets that you can experiment with. Once you found one you like, you can do a lot just knowing the name of the table. So we're not going to write any SQL yet. So I just got the table name. Notice if it has hyphens in it, so we named the BigQuery project with the BigQuery public data with hyphens, that's when you need those backticks. Technically, you only need them around the project name, but that's when you see those backticks, which is that character there, come into play. So if you don't have hyphens anywhere in here, you actually don't need those. That's the first tip for you. Second tip, one of my absolute favorites, if you hold down, at least on this Mac here, it's going to be the Command key or the Windows key. It'll highlight all the data sets in your query. Why is that useful? Because as soon as it's highlighted, you can click on it. So if you have a bunch of different data sets that you just want to explore, or you inherited a query from somebody else, you can quickly get to the schema, the details in the preview of that particular table. So we're going to try to get as far without writing any keystrokes in here. So take a look at the schema. This is San Francisco bike share trips. You've got things like the trip ID, everything we could possibly want. The duration in the seconds, when it started, what stations are, and this is let your kind of mind wander for some of the cool insights that you could take a look at. Geographic data, we've got start, latitude, longitude, end, latitude, and longitude, maybe some of those cool GIS functions. And let's take a look at how many rows we have. We don't have to do count star or anything like that. We have almost 2 million rows and about 375 megabytes into there. And a best practice, you don't want to do select count star from a table limit 10 when just looking at a preview would suffice. So you saw the schema and the data type. Now you can actually go in here, look at all the total rows and see sample data values. So you can see the station, where they stopped and started, everything. That'll get you a familiarity with it. Now, if you wanted to query the table, you can click on Query Table. It'll ask you, hey, I'm going to overwrite everything in the query editor. Sure, that's fine. And it's going to say, select some columns from our bike share trips. Here's a neat tip. It's one I just figured out recently, and props to the BigQuery team. If I just wanted to see, say, the total number of trips that started from the station name, I'm just clicking on the field names, especially if you have field names that are really long, or if you have, you don't want to type things in like I do in a live demo. Then you can just click on these field names and it'll add them. And it'll even add the commas for you, which is kind of cool. And then what you can do inside of BigQuery is you can format the query. Again, even if you're experienced in SQL, this is still kind of fun to try to do as much as you can without even typing anything into the editor. We're going to run that query. It doesn't really do much for us because it's just going to give the station name. It's still at the granularity level of the individual trip. So what's one of the things that you can do inside of BigQuery? If you're looking at that trip ID, we can say, I want to have an aggregate function, like a count of all trips No, it doesn't. It's just counting the rows. You can do count stars. Some people like to put count 1 or something like that. For readability, I'm going to keep the count of trip ID just so somebody else inheriting my code can very quickly see what the level of granularity of this table. And we'll call this the number of trips. Now, naturally, immediately, you're going to get an error. If you work with SQL long enough, as soon as you do an aggregation in one field, all the rest of your other fields better be aggregated as well. But if it's just been a late night, you want to just open up the validator, you can see, hey, this references this start station name. Your other person here is aggregated, but this one isn't. Then you naturally, what you want to do, you want to make sure that you do the group by. And that's how we can say, all right, well, we're rolling up all the trips into a single value. Let's group those by each of the different stations. Now, if you remember your SQL, what's one of the things that you can do to get the most first? You can do an order by, which is going to be a sort. And you can order by the alias, as we see here. Know that you actually can't filter in a where clause by an alias field because it actually doesn't exist when the query engine goes out and performs that where clause. So keep that in mind. That's where you can use things like temporary tables. So orders by the highest number of trips first. We'll just let it say the top 10 stations or something like that. Let's make sure we'll format this. If you want to be a really in Evan's good favor, you can add a comment at the top. This is like the top 10 stations by volume. And go ahead and run that. And we'll see the most popular stations. And we got the San Francisco Caltrain. I can definitely vouch for this one. As soon as you get off the train, you need to get somewhere in San Francisco. And that's got 72,000 trips. Now, if you wanted to experiment a little bit more, what you can do is you can add in a filter and just say, hey, I'm looking for just those trips for 2018. There's another field. We can go back. Hey, honestly, I've already forgotten the field name. I hold down that button, and then I'm going to pop in the start date. Let's take a look at that start date. Start date is a timestamp. So let's see. We can just where the start date is, say after, what did we say, 2018? So we can do 2017, end of 2017. 1231, sure, after all this. You can convert it if you wanted to. Hopefully this will just take automatically. There's a lot of date functions and extractions that you can do, but let's see, I think what was it before, like 20,000 or something like that? 70,000, I think, for the Caltrain. Let's see if the Caltrain is still number one. Ah, look, in the last year, Caltrain is actually dethroned. It's the Ferry Building, super popular tourist spot if you haven't been to San Francisco yet. And that takes the highest number of trips just for 2018. Yeah, if you're doing a lot of this aggregation inside a BigQuery and then filtering, it's fun for these types of insights, but an easier way that you can do it a lot of times is by actually just exporting the data or linking it directly from a front-end visualization tool like Data Studio. So you can actually say, oh, I don't want to actually limit the data here. I want to throw all of it at a visualization tool, and then you can just have a filter for the users that actually has the results. If I wanted to store this common query, I could do a couple of different things. I could save the query as my query inside of my project, personally just for me or for all people that can see it, or I can save it as a view. But what I like to do, since I commonly commit all my code to version control, is I actually do a little bit of data definition language in SQL DDL, and that says I want a creation statement inside of the actual code itself. So people, if they wonder, hey, where on earth did you get this top 2018? And actually, it's not just 2018; it's anything after 2017 as well. For people yelling into their screens like, hey, it's not just 2018. I got you. Create or replace table. And we can just give it a table name. We'll just call, we need a data set. Do we even have a data set? I don't think so. We need to have a data set first before we're just dumping things in here. We could call this Bike Insights or something like that. Data set is just a collection. So now we have an empty data set. There's no tables in there, so we can start populating one. So we have Bike Insights. So create a replace table in the data set, and we'll just call this top trips 2018 and beyond. try to keep your table names a little bit more succinct than mine. And then once you've created that, you should automatically see this show up. Boom, there you have it. And now you can actually have that. The query is not going to be reran every single time. Now, you might be asking, what happens if the BigQuery public data source updates after this? That's an excellent point. So how would your table, this just dumped all of this data here. It's going to be static now. So one of the things that you can do is if you're looking to link this out to your dashboard, instead of creating a table, you could simply create a view, which a logical view, what that means is every single time, and we'll just call this view since it says, hey, that object already exists. Every single time you can notice the icon changes, and you can actually click into here and you can look. Inside of the table, you can actually preview the data. Inside of the view, that preview is gone. Why is that? Because the view is just an empty object. A view is essentially a logical view in this instance of SQL is just a stored query. So if you're trying to query the view, we can query the view, and then that actually just runs against the query that we had stored a little bit earlier. So it's high-level recap. You've seen data sets. You've seen public data sets. You can explore them at your leisure. Some of the neat tips and tricks that you've seen. If you wanted to actually then go in and edit that view later, you can scroll down, bring that result back into here, look back at that schema, and keep exploring as you see fit. This is just the tip of the iceberg when it comes to data analysis. We just did a simple count of trips by the most popular station names. There's also data sets in there for weather, so you can do a fun analysis to see. We have a bike share data set for New York or San Francisco, see where weather affects the riders the most, or how the bike share program is doing as a whole when it comes to seasonality. Is there a lot of more or less ridership in some of the winter months? You can check that all for yourself, but you can do it all with SQL and not have to worry about building any of the infrastructure behind the scenes. All that's managed for you inside of BigQuery. All right, that's a wrap.
As we saw in the demo, a lot of the time you aren't really sure of the quality of the data in your dataset, so you can use SQL to explore and filter for anomalies. Here, we filtered for those customer records who did not provide a birth date by setting member birth year is not null as a filter. I'll provide a SQL syntax reference so that you can bookmark it and refer to it later. While I've been working with SQL for many years, I will freely admit that I don't have all of the functions and clauses committed to memory, and I'm constantly Google searching for that SQL syntax too. If you prefer to use a UI to inspect the quality of your datasets, consider using Cloud Data Prep, which is a GCP product offered in partnership with Trifacta. Using Data Prep, you can load in a sample of your BigQuery dataset into an exploration view, which will then provide you with some neat column histogram charts, as you see here. Now, this specific dataset in this visual is the location of all the weather stations around the world for this specific dataset. The histograms in the state column on the right, they highlight the data that's skewed towards 3 or so values, which we can infer means that there are some states that have many, say a lot of weather stations. Maybe large states like California. You can actually hover over the bars to see the actual values. That's your frequency. What I've highlighted here in the horizontal bar graph is how well the values in a column of data map to the expected data type for that column. DataPrep knows what the allowable or enumerated values for US states should be, and it is telling us that there are 19,940 missing or null values for state. Why do you think that could be? Well, as you might have guessed, these weather station readings could come in from all over the world, and state is an optional field. In DataPrep, if I wanted to create a pipeline to filter all incoming records to only include weather station readings where the country field is equal to the United States or the US, you can use the UI to quickly set up those transformation steps in what's called a recipe. After your transformation recipe is complete, when you run a Cloud Data Prep job, it farms out the work to Cloud Data Flow, which handles the actual processing of your data pipeline at scale. The main advantage to Cloud Data Prep is for teams who want to use a UI for data exploration and want to spend minimal time coding to build their pipelines. Lastly, with Data Prep, you can schedule your pipeline to run at regular preset intervals. But
If you prefer to do all of your SQL and exploration work inside of BigQuery, you can also now use SQL to set up scheduled queries by using the @runtime parameter or the query scheduler in the BigQuery UI. I'll provide a link that shows you how to set up those scheduled queries in the course resources. Now that you're familiar with some of the great insights that you can glean from your data, it's time to talk data security, so your insights are only shared with those people who should actually have access to see your data. As you see here in this table, BigQuery inherits data security roles that you and your team set up in Cloud IAM. For example, if you're an overall project viewer in Cloud IAM, you can start BigQuery jobs, but you cannot create new datasets yourself. If you're an editor, you can create datasets. And if you're an owner, you can also delete datasets. Keep in mind that default access to datasets can be overridden on a per dataset basis. Beyond Cloud IAM, you can also set up very granular controls over your columns and rows of data in BigQuery using the new data catalog service and some of the advanced features in BigQuery, such as authorized views. Data security is more than simply applying the right project permissions and roles during your dataset creation. You should also have a written and circulated data access policy for your organization, and it should specify how and when and why data should be shared and with whom. One first step to ensure healthy data access controls is to periodically audit the users and groups associated with your Google Cloud Platform project and your individual datasets. Do these users need to really be owners or admins, or would a more restrictive role suffice for their job duties? A second pitfall is working with, testing, and editing datasets only in production, much like with code. It's often wise to have a completely separate GCP project or dataset for testing different environments to prevent unintentional data loss or accidental errors. In addition to super fast query execution times, BigQuery also manages the storage and the metadata for your datasets. As we mentioned earlier, BigQuery can ingest datasets from a variety of different formats. Once inside BigQuery native storage, your data is then fully managed by the BigQuery team here at Google, and it's automatically replicated, backed up, and set up to auto-scale for your query needs. You can even recover recently deleted tables within a certain period, too. You also have the option of querying external data sources directly, as we talked about, which bypasses BigQuery's managed storage. For example, if you have a raw CSV file in Google Cloud Storage or a Google Sheet, you can write a query against it without having to ingest the data into BigQuery first. A common use case for this is having an external data source that is relatively small but constantly changes, like say a price list for commodities that another team maintains and continually updates. But there are a few reasons why you maybe should consider not doing this. The first is that the data consistency coming in from that external or federated data source is not guaranteed. If the external data source changes mid-flight, BigQuery doesn't guarantee that those updates were actually captured. And if you're concerned about that, consider building a streaming data pipeline into BigQuery with Cloud Dataflow, which will be the topic that we'll cover in the next module. In addition to ingesting datasets as a batch, like uploading a CSV, you can also stream records into BigQuery via the API. Note that there are a few quota restrictions that you should be aware of. The max row size for a streaming insert is 1 megabyte, and the maximum throughput is 100,000 records per second per project. If you need higher throughput, say in the order of millions of records per second, for use cases you can consider like application logging or real-time events tracking, consider using Cloud Bigtable as a data sink instead. Before you start streaming thousands of records into BigQuery using the API, consider the other options you could have for your streaming solution. If you have data that needs to be transformed or aggregated mid-flight into table and row format, or joined against other data sources as side inputs midstream, or if you want to take just a window or a segment of that data, you should really consider using Cloud Dataflow for your streaming data pipeline. We'll cover working with that solution in the very next module. Lastly, if you're familiar with database design, you've likely heard of the concept of normalization, which is the act of breaking up one huge table into component child tables so you're storing one fact in one place and not repeating yourself across records. Take this taxi company, for example. You could track payments, timestamps of events, and geographic lat longs of pickups and drop-offs, all in separate tables, as you see here. What would you need to do to bring all these data sources together for reporting? If you said do one massive big SQL join, that's absolutely right. But while breaking apart database tables into silos is a common practice for relational databases like MySQL or SQL Server, for data warehousing and reporting, let me show you a cool new way to structure your reporting tables. Take a look at the table at the top. What do you notice that you haven't seen before? First, you have just one row of data, but it looks like you have 4. What's going on? Well, event.time, that field, is actually an array data type. You can have multiple data values, in this case timestamp, for a single taxi booking in that single row. Likewise, with a corresponding array of status values at that timestamp. So already in one table, you get the high level, if you wanted, of total number of orders, but you could also get the number of completed orders without having to do any of those complex joins. The second insight is a bit more hidden, and it's that some of the column names look almost like a family name. Event.status, event.time, or destination.latitude, destination.longitude. These grouped fields are part of a SQL data type known as a struct. If you were to inspect this schema for this table, you'd notice that for the event field data type, it's of data type record, which indicates that this is a data type of a struct. You can think of a struct as essentially a collection of other fields, kind of like a table. From a reporting standpoint, you could have many nested structs within a single table, which is conceptually like having many other tables pre-joined, which would get you excited, into one big table. And pre-joined for you means faster queries for larger data sets, and no more of those complex 15-table joins. Now, a huge benefit of doing it this way is that you have a single table which has all the fields in a single place for you to analyze. You don't need to worry about the join keys or differing levels of table granularity anymore. BigQuery natively supports GIS, or Geographic Information System, functions for gleaning insights from your geographic data points, like longitude and latitude. Let's examine how you can put these into practice. In this SQL query that you see here, we are plotting the path of a hurricane using SQL and GIS functions. We first create a geographic point based on lat-long data. We also bring in other useful fields, like wind speed, the distance the hurricane is to land or landfall, and the radius of the hurricane. We query all this raw data from the BigQuery public dataset from NOAA on hurricanes and filter for one hurricane in particular. You can see that in the where clause. That's Hurricane Maria in 2017. Then we geographically bound the points that we care about with the GIS within function to ensure that it'll fit on the map or the area of focus so we can visualize these points. Lastly, we explore our points using GeoViz, which is a web tool for visualization of geospatial data in BigQuery, but it uses the Google Maps APIs. Here you can see and track the hurricane making landfall in the US. One of the best ways to get better at data analysis is by practicing on a variety of datasets. The BigQuery Public Datasets program partners with companies and organizations to host their datasets in BigQuery and then make them available for analysis by the public. Currently, there are well over 100 different datasets for you to explore, and you can find them all in the BigQuery web UI under Explore Data, which is located right above your own datasets. So let's do a quick activity. Explore a BigQuery public dataset that interests you, and then think of the following questions to answer. What's the name of the dataset? How many records are in some of the tables? Are there any data quality concerns after you previewed that data? And after analyzing the schema, what types of insights do you think you could find? Lastly, are there any other data sets that you could potentially join against this one for additional insights? Take a moment to find and explore your dataset, and then we'll bring in the head of Google Cloud BigQuery Public Datasets program, Shane Glass, and he'll explore one of his favorite BigQuery public datasets in a demo.
Hi, my name is Shane Glass, and I'm the Program Manager for Google Cloud's Public Dataset Program. And I'm here today to talk to you about the public datasets we have available in BigQuery and Google Cloud Storage, as well as how they can support your workloads. And don't worry, there's a fun demo at the end too. Now, the mission of our public dataset program is quite simply to maximize the availability and accessibility of high-value, high-demand public data assets through Google Cloud. And we do this because we fundamentally believe that it makes life a little bit easier for our users. We currently have more than 130 datasets in our public dataset program, and these datasets are onboarded and maintained by Googlers with provider input and guidance. You can see here a sample of our data providers, including NOAA, the U.S. Census Bureau, the United Nations Statistics Division, the Federal Elections Commission, and others. We're constantly adding new datasets, and here are just 3 examples of recently added unstructured datasets, all coming from NOAA, the National Oceanic and Atmospheric Administration. They include a high-resolution rapid refresh weather model, the new GOES-16 satellite imagery, and NOAA's National Water Model that provides stream flow information across the continental United States. We also have datasets in BigQuery, including the GitHub repository, the NOAA Global Surface Summary of the Day that provides meteorological observations going back to 1900, and the Ethereum blockchain, along with 6 other cryptocurrencies. But don't just take my word for it. Let's see a demo, specifically looking at how you can use some of our geospatial datasets to support your workflows. So let's look at a demonstration that tells you how many lightning strikes there were across the continental United States in 2018, thanks to the lightning data we have available from NOAA. You can see here a query that runs real quickly, and it'll give you a concatenation in a little bit cleaner format so that it's easier to visualize this data in Data Studio. So we'll click Run down here, and a little like they do in the cooking shows, I already have it finished. You can see here the number of lightning strikes with a center point of a 1/10 degree by 1/10 degree tile that aggregates the strikes across the US. We'll take a look in Data Studio and see what we notice trend-wise. We'll flip over to our cooking show finished version, and you can see here the aggregated number of lightning strikes across a year on average. But this doesn't really tell us much, as it's hard to see the specific data points. So let's zoom in using the zoom area function in Data Studio. And we'll zoom in to the United States, and this is primarily where the data comes from. Now, I had originally expected Florida to have the most lightning strikes per day, but as you can see, what really stands out on this map is the collection of data here in Oklahoma. Now, I'm curious, and I want to dig in further, and how can you use public datasets to do that? Now, we can use the geospatial capabilities, or GIS, that are built into BigQuery. And this helps BigQuery understand the geospatial relationship between datasets. Now, this particular query has a little pre-processing done under the hood, but we're hopeful to make that unnecessary here in the near future. For now, we'll take the shortcut. And so this query gives us the return of a polygon for each tile, as well as the number of lightning strikes by day. But let's say we wanted to look at that in a more visual format. Well, I'd come over to BigQuery GeoVis, the geovisualization capability available for free. I could come down here and run the same query, see my results, and define which column is our geometry. And from there, I give it a style that best fits our data. In this case, I've given an interval for the number of strikes and the location. And I can tell you, as a former Oklahoma resident, this makes a lot of sense to me. The areas of Oklahoma that are notorious for the storms are also seeing the greatest number of lightning strikes. But this is pretty broad. These are 1/10 of a degree by 1/10 of a degree tiles across the state. Well, what does that actually mean? No one measures the world in 1/10 of a degree tiles. Instead, we define the world by boundaries. In most cases in the US, political and statistical boundaries, such as either counties or census tracts. In this case, let's take a look at one of the 10 boundary datasets we have available in BigQuery through the public dataset program that defines the space around each of these borders. In this case, we'll start with counties, since that's a pretty popular one in Oklahoma. We'll run a pretty similar query, except this time we'll take a little shortcut so that I only have to remember the state name as opposed to the state FIPS code. And again, we'll run our results and we'll see the counties. This time is the geometric column. And again, we can run our visualization and add style that meets the needs of our data set. And one of the nice features about BigQuery GeoViz is it allows me to go in and click on an individual county and see what the exact outputs were. And we can see here, for example, that Oklahoma County has about 300 lightning strikes per day. And this pretty closely lines up with what we saw from the other map, except on a more understandable boundary. What if we wanted to look at something more granular though? Say, for instance, zip codes. Again, we'll take the same data set, but this time we'll define it by the spaces of zip codes, or zip code tabulation areas in this case. And we'll run that through, and that gives you a better idea of maybe what zip code you want to avoid, assuming you don't like lightning strikes. We'll go through the same process, and we'll define the same style. This time, let's use a different method of defining that data-driven column. So let's use a linear extrapolation. We'll give it a low of 27, as you can see the minimum down here, and then we'll go up by 100 from here. So 120, 220, 320, and so on, and I'll want to get over my max of 499. I'll quickly set the colors down here, and I can scroll through some different options to find one that suits my palette. In this case, I want to use something pretty similar to the one I used in the counties. And you can see here, again, there's a dark concentration here around Oklahoma City. But this time, I can drill down to a more granular level and see which zip codes might make it the most likely for me to see some lightning strikes in my backyard. So this is just one example of what can be done with public data sets. If you're interested in learning more and figuring out how you can join public data sets with your private data sets, I encourage you to check out GCP Marketplace and click on Datasets on the left-hand side. There, you can learn more about datasets and get started in BigQuery today.
It's time to revisit the exciting topic of machine learning. Previously in this course, your data science team had to build a recommendation model using Spark ML that you then ran on Cloud Dataproc for scale. Later in this module, you're going to be building custom models yourself with just SQL using BigQuery ML. But before we jump into the code, we need to expand our machine learning foundation and then cover the models and the key terminology that you need to know before we set you off to make predictions. When people think of AI or machine learning, they generally think of the advanced models like you saw earlier on Google Photos video stabilization and the smart reply feature in Gmail. And yes, later in this course, you will build image models on unstructured data sets. But did you know that at Google, the majority of the models deployed are models that operate on structured data? These aren't your 50-plus layer deep neural networks that play StarCraft or chess. They're built on rows and columns of data, just like you've seen and experimented with inside of BigQuery. So, if you have a structured data set that you think is a good use case for machine learning, the next step is to find a model type that is appropriate for your use case. Out of all the models out there, what's a good place to start for you to start prototyping? Here's a decision tree, no pun intended, to help guide us. We'll walk through each of the different branches. The first question is what kind of activity that you're engaging in. Is there a right answer or a ground truth that exists in your historical data that you want to model and then predict? If so, you want to start with supervised learning. Alternatively, if you're interested in just ruminating and exploring the data for unknown relationships, you're welcome to try unsupervised learning with maybe a clustering model to start. Unsupervised learning is outside the scope of this course, but I'll link you to a few resources to show how you can do it quickly with a clustering model inside of BigQuery ML. The majority of the problems we're going to tackle here are in these three areas. First, forecasting. That's like predicting the next month's sales figures, the demand for your product. Second, classifying, like high, medium, or low risk events, or buy or no buy decisions. And third, maybe recommending something like a product for a given user. An easy way to tell if you're forecasting or classifying is to look at the type of label or special column, we'll cover that more later, of data that you're predicting. Generally, if it's a numeric data type, like units sold or profits earned, you're doing forecasting. If it's a string value, you're typically doing classification. This row is either in this class or this other class. And if you have more than 2 classes or buckets, like high, low, medium, you're doing what's called multi-class classification. Now, once you have your problem outlined, it's time to go shopping for models, which will be the tools to help you achieve your goal. Now, there are many different model types for you to choose from for these problems. We're recommending you start with the simpler ones, which can still be highly accurate, to see if they meet your benchmark. By the way, your ML benchmark is the performance threshold that you're willing to accept from your model before you even allow it to be near your production data. It's critical that you set your benchmark before you train your model, so you can really be truly objective in your decision making to use the model or not. Now on to types of models. For forecasting, try out linear regression. For classification, try logistic regression. By the way, it's called binary logistic regression if you have just 2 classes or buckets that an observation can fall into, or multi-class if it's more than 2. For recommendations, try matrix factorization, which is a commonly used algorithm for problems involving a matrix of users and items, like your housing rentals example. Now here's the complete picture again. You'll see later with BigQuery ML that you can just specify model type equal to linear regression, for example, and BigQuery handles the rest for you. What didn't you see here that you might have heard of in terms of a model type? There's many different types of models out there that you may not see on this chart. More complex models like deep neural networks, decision trees, random forests are also available for modeling. You'll even build a custom model using neural architecture search to build a deep neural network later on in this course, and you'll do so without using any code. That's with AutoML. It's my overall recommendation that even if you know how to build advanced models, that you start with the simpler ones first, because they often train faster, and they give you an indication of whether or not ML is even a viable solution for your problem. Now that you're familiar with the types of model to choose from, we need to feed in high-quality training data for them to learn. That's the learn part of machine learning. Machine is the tool or algorithm like linear regression, and the learning is the insights that the model has into the relationships between the known and unknown data. That's why we call it modeling. You're trying to approximate reality based on what you do know. The best way I've found to learn the key concepts of machine learning on structured datasets is with this quick example. Here, our scenario will be predicting customer lifetime value with a model. Lifetime value, or LTV, is a common metric in marketing, which is where we'll estimate how much revenue or profit we can expect from a customer given their history or customers with similar patterns. The dataset that we'll use is a Google Analytics e-commerce dataset on Google's very own online merchandise store that sells swag like t-shirts and other products that you see listed here. Our goal is to target high-value customers with special promotions and incentives. After exploring the available data, we came up with a few fields that we thought might be useful to the model and to determining whether or not a customer is high value based on their behavior with our website. These fields include how many lifetime page views, how many total visits, what's the average time that they spend on our site, and what the total revenue that they've brought in is, and the count of their previous transactions with us on our site. Now that we have some data, and note, we'll need a lot more than just the 7 records that you see here. It would be more like on the order of tens of thousands. Then we can get ready to feed it into our model. But before we do, we need to define our data and columns in the language that data scientists and other ML professionals use. Taking the e-commerce example we had in the previous lesson, a record or a row is an instance or an observation. In this picture that you see here, we have 8 instances. A label is the correct answer that's known historically, like how much this particular customer spent. And that's the field that's in the future data is unknown or missing, hence the model training and prediction. For example, if we know that a customer who has made transactions in the past spends a lot of time on our website, often turns out to have a high LTV for revenue, we could predict the same for newer customers who are on that same spending trajectory. Here we're forecasting a number. So do you remember which model type we should use? If you said linear regression as a starting point, that's exactly right. Now notice how I didn't say that if transactions are greater than 10 for this row, then you could expect the revenue to be greater than 1,000. Remember that in an ML, we feed in columns of data and then let the model figure out the relationship to best predict that label. It may even turn out that some of the columns are not useful at all to the model in predicting the outcome. And I'll show you how you can find this out later by inspecting what the model actually learned. Labels could also be binary values, like if they're a high-value customer or not, as shown here. Knowing what you're trying to predict, the class, the number, again, that'll greatly influence the type of model that you're going to choose. So we've got our label field there on the right as high-value customer or not. So what do we call all these other data columns in our table? Those columns are called features, or potential features at least. Those are our inputs to the model. Each column of data is like a cooking ingredient that you can use from your kitchen pantry. As my young daughter often finds out, cooking with all of the ingredients can often spoil your dinner. It's the process of feature engineering. You got to whittle it down. Now that sifting process where you're going through your data, that's where you're going to expect to spend the majority of your time as a data analyst, engineer, or even a data scientist. And it's an art form as much as it is a science. Understanding the quality of the data in each column and working with other teams to get more features or more history is often the hardest part of any ML project. You could even combine or transform these features in a process called feature engineering. It sounds fancy, right? Well, if you've ever created calculated fields in SQL, like combining columns together, you've just done some basic feature engineering. Also, BigQuery ML does a lot of the hard work for you, like automatic one-hot encoding of categorical variables, and things like splitting your dataset into training and evaluation automatically too. Let's talk now about predicting on future data. Say some new data comes in that you don't have a label for. You don't know whether or not these new customers will have a high LTV or not, but you do have a rich history of labeled examples for your model to train on. So we can train a model on the known data up top, and then once trained and we're happy with the model's performance, we can then use it to predict on that bottom set of data, that unknown data. It's now time to cover how you can create these models with SQL in BigQuery. And we'll review what the project phases you can expect to hit along the way too. If you've worked with ML models before, you know that building and training them can be very, very time intensive. For a common data scientist, you must first export small amounts of data from your data store into your IPython notebook and into data handling frameworks like Pandas for Python. And if you're building a custom model, you first need to transform and pre-process all of that data and perform all that feature engineering before you can even feed the model data in. Then, finally, after you've built your model in, say, TensorFlow or another similar library, then you train it locally on your laptop or on a VM. Doing that with a small model then requires you to go back and create more new data features and improve performance. And you repeat and repeat and repeat. And it's hard, so you stop after a few iterations. Also, I mentioned IPython notebooks in Python. In the past, if you weren't familiar with these technologies, ML was left to the data scientists of your team and out of your reach. But now you can do ML on your structured data sets inside of BigQuery using SQL in just a few minutes. Take a look at how you can perform ML in BigQuery with just a few steps. Step 1, you create the model with just a SQL statement. Here, we'll use a bike share dataset. Step number 2, write a SQL prediction query and invoke ml.predict. Step number 3, profit. That's it. You've got a model and then you can view the results. Well, in reality, there are more than 3 steps. Like you have to evaluate the model, right? But the main point is that if you know basic SQL, you can now do machine learning, which is pretty cool. BigQuery ML was designed with simplicity in mind. To that end, you don't have to define the ML hyperparameters, which is a fancy way of saying the knobs that are set on the model before the training starts, like things like the learning rate, or even the split between training and test data, which is critical. BigQuery ML automatically does that for you with default values. In addition, with the model options, if you wanted to, you could also set yourself the those regularization or different strategies for splitting or testing the data, and manually setting the learning rate and other different parameters, hyperparameters. So, what do you get out of the box? First, BigQuery ML runs on standard SQL. It's inside of BigQuery. So you can use normal SQL syntax like UDFs, user-defined functions, subqueries, and joins across other different tables to create your training data sets to feed into the model. Now for model types, right now you can either choose from linear regression for forecasting or binary and multi-class logistic regression. And the team is busy, very busy, adding more types as we speak. So I'll provide a link so you can stay on top of that documentation. As part of your model evaluation, you'll also get access to fields like the ROC curve, as well as accuracy, precision, and recall. This is for classification models that you can simply select from with a SQL statement after your model is trained. Or if you don't want to write any code, you can click on the UI, click on that trained model, which is now an object inside of your data set, and there's a tab for that evaluation that you can take a look at as well. And one of my favorite things is you can also inspect the weights of the model and perform a feature distribution analysis. Now we'll get into that a lot more later. Next, let's walk through the phases of a typical BigQuery ML project. Let's walk through the key phases of your ML project in BigQuery. What you'll find is that writing the code to create the actual model is going to be the really easy part. Getting all the right data into the model is always the hard part. The entire process is going to look like this. First, we need to bring our data into BigQuery if it isn't there already. Here, again, you can enrich your existing data warehouse with other data sources by simply using SQL joins. If you're already using other data products like AdWords or YouTube, you can look out for those easy connectors to get that data into BigQuery before you go off and build your own pipeline. Next is the feature selection and pre-processing step, which is similar to what you've been exploring so far as part of this course. Here is where you put all your good SQL skills to the test in creating a great training set for your model to learn from. Keep in mind, again, as we mentioned, that BigQuery ML does some of the pre-processing for you, like that one hot encoding of your categorical variables into those numeric values that your model actually is expecting. After that, here's the actual syntax for creating a model inside of BigQuery. And it's short enough that I could fit it all inside this one tiny little box of code. You simply say, create model, give it a name, specify the mandatory option, like model type, and pass in your SQL query with your training data set, then hit run query and watch your model run. After your model is trained, you'll see it as a new dataset object in BigQuery, which you can actually click on and look at all those cool metadata stats. Or if you wanted to write the query against it to look at the evaluation, then you use ml.evaluate to evaluate the performance of your trained model against the evaluation dataset. Here, you can analyze loss metrics like root mean squared error, MSE or RMSE, for forecasting models, and other metrics like area under the curve, accuracy, precision, recall for your classification models, like the one that you see here. Once you're happy with your model's performance, you can then predict with it with this even shorter query. Just write and invoke the ml.predict command on your newly trained model, and then you'll get back predictions as well as the model's confidence in those predictions. Now you'll notice a new field in the results when you run this query, where you'll see your label field with the word predicted added to the field name. And that's your model's prediction for that label. Now that you're familiar with the key phases of your ML project, it's time to walk you through some of my favorite advanced features of BigQuery ML. Recall that you can create a model with just create model. If you do want to overwrite an existing model, you can do create or replace model. Models, again, take options, which you can specify if you want. The most important and the only required one is that model type. Linear regression for forecasting, logistic regression for classification, with many more types coming soon. I'll add a little link in the resources where you can view all of the available model options. You can set things like the model learning rate for how fast it should learn, and even hyperparameters for things like regularization to prevent overfitting. To evaluate the model's performance, Next, you could just run simply ml.evaluate against a trained model. You'll get different performance metrics as we covered, depending upon the type of model that you choose. Also, you can look at the model's performance in the UI just by clicking on the model object in your dataset and taking a look at all that available metadata. I do that pretty often because I'm pretty lazy in BigQuery. Making predictions is as simple as calling ml.predict on a trained model and passing through the dataset that you want to predict on. Now, let's do one final big review and what I'll call the cheat sheet. If you're going to print something out, it's going to be this page. First, in BigQuery ML, you need to have a field in your training dataset titled label, or you need to specify which field or fields are your labels by using the input label calls in your model options. Second, your model features are simply the data columns that are part of your select statement after your create model statement. After a model is trained, you can use ml.featureinfo to get statistics and metrics about that column for additional analysis. Next is the model object itself. You train many different models, which will all be based on objects stored inside your BigQuery dataset, much like your data tables and views. Try clicking on a model object, and it can view information about when it was last updated or how many training runs it completed. Creating a new model is as easy as running create model, choosing that model type, and passing in a training dataset. And again, if you're predicting on a numeric field, like sales for next year, consider looking at linear regression for forecasting. If it's a discrete class, like high, medium, or low, spam or not spam, consider using logistic regression for classification. While the model is running, and even after it's complete, you can view training progress with ml.traininginfo. As we mentioned previously, you can see what the model learned about the importance of each feature as it relates to the label that you're predicting. Again, this is my favorite part. Those are what's called your model's weight. You can see how well the model did against its evaluation dataset by using ml.evaluate. Lastly, it's as simple as writing ml.predict in referencing your trained model and then your prediction dataset to return back predictions. An important note here is that when using ml.predict and passing in a new dataset with an unknown label, that you can now add other columns that you didn't want to train on initially. The model is not being retrained naturally during prediction. Note that if you do happen to remove or rename columns from your prediction dataset that the model was expecting that it saw in training, you'll be given an error. So the 4 major steps look like this. Write a SQL query to extract training data from BigQuery. Create a model specifying that type. Evaluate the model and verify that it meets the requirements. And then predict on that model using data that's extracted from BigQuery. And if you're explaining BigQuery ML as a whole to others, I often just list these main points. So as a broad recap, BigQuery ML allows you to write machine learning models with SQL, experiment and iterate right where your data lives inside of BigQuery. Currently, build classification, both binary and multi-class, and forecasting models, with more model types coming soon. And if you know machine learning already, you can really get into the details of your model options and weights very easily. Common adjustments that you can make above and beyond what BigQuery ML defaults to everyone include things like the learning rate, regularization, the training evaluation dataset split, predefined weights for classes, and much, much more. Check out the BigQuery ML documentation link and bookmark it as a reference, especially as new features continually be added. So far in our course, the data that we've been looking at has been loaded in batch form, coming from pre-existing structured datasets like Cloud SQL or BigQuery. But what about if the data is on thousands of sensors, streaming in data points worldwide? What if they send new messages every minute or even faster? How can you harness such upstream data sources for your analysis? Welcome to the module in real-time IoT dashboards, where we'll highlight and solve the challenges of streaming data processing. We'll first look at the challenges that give today's data engineers headaches when trying to set up and manage their own pipelines. Then we'll examine how we can capture all of these streaming messages and wrangle them in a reliable, global, and scalable way into our pipeline. After we've captured the streaming messages, we'll show you how you can build serverless data pipelines for streaming that data using Google Cloud Platform tools. You may be asking, serverless? How can I design and control the pipeline for scale if I need to? And we'll cover all of that in our sections on Apache Beam and Cloud Dataflow, which are popular ways to design and implement these kinds of pipelines, respectively. Last, once we've captured, processed, and then stored the data, we'll then see how we can visualize our insights with reporting dashboards. Building scalable and reliable pipelines is a core responsibility for data engineers. In modern organizations, data could come in from all different data sources. Imagine a gaming company that tracks high scores for users from their events, and it needs to log player progress towards in-game objectives. Or hundreds of distributed IoT sensors reporting weather readings from all around the globe. What about point-of-sale data from 1,000 different storefronts? How do we alert our downstream systems of new orders in an organized way and with no duplicates? Now, let's amplify the magnitude of the challenge to handle not only a variety of input sources, but at a variable volume of data that can start at gigabytes and scale up to petabytes or more. Will our pipeline code and infrastructure scale with it, or will the pipeline grind to a halt or crash? And we need to do it all near real time as soon as that data touches our system. Oh, and by the way, we need a way to handle if our data arrives late, it has bad data in the message, or if it needs to be transformed mid-flight before we can stream it into our data warehouse. Are you pulling your hair out yet? I actually don't have that much hair left to pull out. Well, as you can start to see, there are significant challenges at every turn for the pipeline developer. We'll unpack each of these challenges, and hopefully by the end of this module, you'll not only have the peace of mind knowing that there are solutions out there, but also the real-world experience building a streaming data pipeline on IoT data for your lab. Let's now discuss one of the first pieces in the pipeline puzzle, which is handling large volumes of streaming data that won't be coming in from a single structured database. Instead, those event messages could be streaming in from 1,000 or 1,000,000 different events, all happening asynchronously. A common use case where you see this pattern occur is with IoT, or Internet of Things applications. IoT devices could be the sensors on Gojek's drivers' motorcycles that you saw earlier that send out that location data every 30 seconds for every single driver. Or they could be temperature sensors placed throughout a data center to optimize and measure heating and cooling costs. Whatever the use case is, we have to tackle these four primary components. Streaming data from various devices or processes that may not even talk to each other, and even they could send bad data or data that's delayed. It's number one. Number two, we need to have a way of not only knowing and collecting these streaming messages in some sort of buffer, but also allow other services to subscribe to new messages that we're publishing out. Naturally, the service needs to handle an arbitrarily high amount of data so we don't lose any messages coming in. And it has to be reliable. We need all the messages, and also a way to remove any duplicates if found. One tool to handle distributed message-oriented architectures, like what we've been talking about, at a scalable way is Cloud PubSub. The name is easy to remember because it's the publisher-subscriber model, or another way of thinking about it is Cloud PubSub publishes messages to subscribers. At its core, PubSub is a distributed messaging service that can receive messages from a variety of different streams, upstream data systems like gaming events, IoT devices, application streams, and more. It ensures at least once delivery of messages and passes them to subscribing applications, and no provisioning is required. Whether it's a ton of messages or none at all, PubSub will scale to meet that demand. Also, the APIs are open, and the service is global by default, and offers end-to-end encryption for those messages. Here's what an end-to-end architecture could look like. Upstream data starts in from the left and comes into those devices from all around the globe. It's then ingested into Cloud PubSub as the first point of contact with our system. Cloud PubSub reads, stores, and then publishes out to any subscribers of this particular topic, we'll talk about topics soon, that these new messages are available. Cloud Dataflow, as a subscriber to this PubSub topic in particular, can then say, hey, you got messages? Let me take them. It'll ingest and transform those messages in an elastic streaming pipeline. And you can output those messages wherever you want. If you're doing analytics, one common data sink is Google BigQuery. And lastly, you can connect a data visualization tool like Tableau, Looker, or Data Studio to visualize and monitor the results of your streaming data pipeline. Next, we'll talk more about the architecture of PubSub. A central piece of PubSub is the topic. You can think of a topic like a radio antenna. Whether your radio is blasting music or it's turned off, the antenna itself is always there. If the music is being broadcasted on a frequency that no one's listening to, the stream of music still exists. Similarly, a publisher can send data to a topic that has no subscriber to receive it. Or the inverse. A subscriber could be waiting to hear data from a topic that isn't getting any data sent into it. And that's kind of like listening to all that static on a bad radio frequency. Or you could have a fully operational pipeline where the publisher is sending data to a topic that an application has subscribed to and is pulling from. To recap, there can be 0, 1, or many publishers, and 0, 1, or many subscribers relating to any given PubSub topic. And they're completely decoupled from each other, so they're free to break without affecting their counterparts. It's best described in an example. Say you've got an HR or human resources topic. A new person joins your company, and then this notification should allow other applications that care about a new user joining your company to subscribe and then get that message when it happens. What applications could tell you that a new person just joined? Well, you might have two different types of workers, full-time employees or contractors. Both sources could have no knowledge of the other, but still are equally pushing their events saying, this person just joined, into the PubSub HR topic. What other areas of your business do you think would like to know as soon as a new person joins your organization? Once PubSub receives the message, downstream applications like the company's directory service, the facilities system, account provisioning, and badge activation systems can all listen in and process their own next steps independent of one another. PubSub is that good solution to buffering changes from those lightly coupled architectures like this one here with many different upstream sources and potentially many different downstream sinks or subscribers. It supports many different inputs and outputs, and you can even publish from one PubSub event from that topic to yet another PubSub topic should you wish. For our application, we want to get these messages reliably into our data warehouse. So now we're going to need a pipeline that can match PubSub's scale, and it has the elasticity to do it. Now that we've captured all of our messages from a variety of different streaming input sources, we need a way to pipe in all that data into our data warehouse for analysis. Here's a quick mental framework for the two problems that we need to solve as a data engineer building our pipeline. Much like an architect drawing a blueprint and then eventually building the house or building, we have to solve for, number one, the design of the actual pipeline in code. Number two, the actual implementation and serving of that pipeline at scale in production. Here are some of the common questions to ask in each of these phases. For pipeline design, is the code we're going to write compatible with both batch and streaming data, or would we need to do any refactoring? Does the pipeline code SDK we're using have all the transformations, mid-flight aggregations, and windowing functionality? And does it have the ability to handle late data coming into the pipeline? Lastly, for design, are there any existing templates or solutions that we could leverage to quickly get us started? One popular open source solution that we talked a bit about earlier in the course is building pipelines with Apache Beam. It works with both batch and streaming data, and has an ever-expanding list of transformations and functions that are committed and added to its open source repository. Best of all, for this class, is that you'll be starting from an existing template for your pipeline code. So what exactly is Apache Beam? And what does a pipeline written using the SDK look like? Apache Beam is a portable data processing programming model. It's open source, and it can be ran in a highly distributed fashion. It's unified, in that a single model, meaning your pipeline code, can work for both batch and streaming data. You're not locked into a vendor, because the code is portable and can work in multiple execution environments like Cloud Dataflow or Apache Spark, among others. It's extensible and open source. You can browse and write your own connectors and build transformation libraries too, if you wanted. Apache Beam pipelines are written in Java, Python, or Go. The SDK provides a host of libraries for transformations and existing data connectors to sources and sinks. Apache Beam creates a model representation of your code, which is portable across many runners. Runners pass off your model to an execution environment, which you could run on many different possible engines. Cloud Dataflow is one of the popular choices for running Apache Beam as an engine. Here's what an actual pipeline looks like using the Apache Beam SDK running on Cloud Dataflow as an engine. Each step in the pipeline does a filter, a group, transform, compare, join, and so on. Now the critical point is that transformations can be done in parallel, which is how you get that truly elastic pipeline. In the code snippet here, c.element gets the input, and then c.output sends the output to the next step of the pipeline. You can get input from many different and even multiple sources concurrently, and then you can write output to many different sinks, and the pipeline code remains the same. You can put this code inside of a servlet, deploy it to App Engine, and schedule a cron task queue in App Engine to execute the pipeline code periodically. But what if you didn't want to manage the infrastructure running the pipeline? We'll see now how next you can implement your pipeline code at scale with low maintenance. Now that you've seen the pipeline design and code, it's time to talk about implementing it at scale for your production data pipelines. When shopping around for execution engines for your pipeline code, consider these questions. How much maintenance overhead is involved? Is the infrastructure itself reliable? How is scaling handled? How can I monitor and alert on things in my pipeline? And am I locked into a vendor? With Cloud Dataflow, a lot of the complexity of infrastructure setup and maintenance is handled automatically for you. It's built on top of Google's infrastructure, and it auto-scales to meet the demands of your data pipelines. It's also tightly coupled with other Google Cloud Platform projects like Stackdriver, so you can set up priority alerts and notifications to keep a watchful eye on your pipeline and the quality of data that's coming in and out. You can replace all the various data handling tools with just Dataflow. Many Hadoop workloads can be done easily and more maintainably with Dataflow. Plus, Dataflow is serverless and designed to be no-ops. What do we mean by serverless? It means that Google will manage all the infrastructure tasks for you, like resource provisioning and performance tuning, as well as ensuring that your pipeline is reliable. That means you can spend more of your time analyzing the insights from your data sets coming out of the pipeline and less time provisioning resources to ensuring that your pipeline will actually make it through its next couple of cycles. It's designed at its core to be low maintenance. So, what does Cloud Dataflow do with a job? Once it receives it, the Cloud Dataflow service optimizes the execution graph of your model to remove inefficiencies. It schedules out work in a distributed fashion to new workers and scales as needed. It will auto-heal in the event of faults with those workers. It will rebalance automatically to best utilize the underlying workers. And it'll connect to a variety of data syncs to produce a result. BigQuery is just one of the many syncs that you can output data to as you'll practice inside of your lab. What you won't see by design is all the compute and storage resources that Cloud Dataflow is managing for you elastically to fit the demand of your streaming data pipeline. That's fully managed. And even if you're a seasoned Java or Python developer, it's still a good idea to start from many of the existing Dataflow templates that cover common use cases across Google Cloud Platform products. See whether or not there's an existing template for you to work from. For IoT use cases, PubSub through Dataflow into BigQuery already exists, and it's a popular choice. Here's a quick recap of Cloud Dataflow. It's designed to be easy to deploy your pipeline and have it just run. It's serverless and fully managed. The same code can do both batch and streaming at scale. It's built on Apache Beam's open source programming model. And it can auto-scale, auto-heal, and rebalance to millions of queries per second. While data sitting in BigQuery is great if you're an analyst or exploring for insights with SQL, but it's often not enough for your stakeholders who want to see and interact with your data in a more intuitive and visual way. Data visualization is a powerful tool to let you explore your data also before presenting your results. Speaking of exploration, a new and popular way to explore your datasets is available right within BigQuery. After you execute a query, you can explore in Data Studio to immediately start creating visuals or explore as part of building a dashboard. Now here's an example of an actual Data Studio report. Now you don't have to understand the numbers, but just on the surface, what do you think this report is trying to do? In this case, it was the ad performance for the 2016 Olympic Games that were broadcasted on NBC. The role of your report should be to highlight the key insights that your audience cares about. Don't show them everything. Focus and filter their attention to just what those data points or those insights that they need to be seeing right then. Telling a good story with your data on your dashboard is critical because your users are likely not going to care about that amazing pipeline you just built if the output of the dashboard is ugly and hard to use. Take it from experience. Data Studio comes with pre-built templates like this one that monitors your GCP billing in a dashboard. You can even connect this one to your own GCP account to monitor your own spending and do some fun analysis like track incoming BigQuery jobs and the amount of data that those queries are processing. Here's a quick walkthrough of the Data Studio UI. Now keep in mind that the team is continuously updating the product, so refer to their documentation as a link for those best examples and additional practices. The Data Studio homepage shows the dashboards and the data sources that you have access to. Now, it's an important distinction between the two. Connected data sources can feed into dashboards, but just because somebody has access to your dashboard doesn't mean they automatically are granted permission to view the underlying data that's presented, because that could be controlled in BigQuery or elsewhere in your GCP project. Anyway, there are two ways to create a new report from scratch: from the templates panel up at the top, or from the button in the lower right-hand corner. The first thing you need to do is tell Data Studio where your data is coming from. And that, again, is known as the data source. A Data Studio report can have any number of data sources, but we'll just start with one. The data source picker shows all the data sources that you have access to. Note that you can have any or all of these data sources in a single Data Studio report. Since Data Studio reports and datasets can be shared, you should be aware of the ramifications of adding a new data source. When you add a data source to a report, Other people who can view the report can potentially see all the data in that data source if you share that data source with them. And anyone who can edit the report can also use all the fields from any added data sources to create new charts with them. You can click Add to Report to connect the data source, and then you're ready to start visualizing. Now let's look at some tips and tricks for chart creation. The mantra in Data Studio is click and draw, not drag and drop. So you select a chart type, then you draw a box where you want it to go. Data Studio automatically adds some appropriate fields that it thinks could be useful to your chart. The Chart Properties panel on the right is where you can configure your chart. You can give your report a name just by clicking on the title and editing it. One thing to watch out for, since Data Studio is based on Google Drive, you can have duplicative file names. Click View to see what your users will ultimately see. And here's our report. Notice it looks very similar to when you were editing it, but as a viewer, you can't modify the report. Note that you can mouse over any of the charts and graphs on the report. This is live data. It's not just a static image. So this report may not look like much, but with just a few mouse clicks, you can connect to a data source like Google Analytics and create a chart graphing session data over time. A few more key things to know. Dimension chips are green. Dimensions are things like categories or buckets of information. Dimension values could be things like names, descriptions, or other characteristics of a category. Metric chips are blue. Metrics measure dimension values. Metrics represent measurements or aggregations, such as a sum, x plus y, a count, how many of x, or even a ratio, x over y. You can even create simple metrics through calculated fields, like field 1 plus field 2. These can be much more complex, using over 50 calculated field functions available in Data Studio. A calculated field could also be a dimension. For example, you could use a regular expression to extract part of a landing page URL or a keyword into a new dimension to make it easier to read. Lastly, you can share and collaborate your dashboards with your team. Keep in mind that when you share a report, if you're connecting to an underlying data source, like a BigQuery dataset, Data Studio does not automatically grant permissions to viewers in that data source if the viewer doesn't already have them. This is for data security reasons. After you share your report, users can interact with filters and sort, and then you can collect feedback on the usage of your report through Data Studio's native integration with Google Analytics. Now let's take a look at how you can visualize your insights on top of a dashboard. So earlier we took a look at the bike share trips data inside of BigQuery. And one of the things that I want to highlight before we jump into the dashboard building is when you click on a data set inside of BigQuery, there's a native integration with Data Studio. Naturally, you know on the Data Studio side, you can create a data source, but did you know inside of BigQuery, you can actually click on the table. Under Export, there's this new option called Explore in Data Studio. And this is just the raw table being passed in as a data source. It's kind of an in-between. This is called the Explorer view, and it's a great way for exploration. Immediately, intelligently, Data Studio says, hey, these are some interesting fields that you might want to visualize, like the originating station name and the total amount of trips there. So you can see the Caltrain station is just dominating it for Townsend and Forth. That's one of the last stops in SF. 72,000 trips. And if you said, hey, I didn't want a table, I want to see a bar chart, maybe sorted, and you can just see the clear dominance of the Caltrain station there. And you can, maybe you're wondering, hey, has that always been the case? Instead of doing a filter on the where clause, you can actually just create a filter here. Start date. Let's see what our options are. I don't want to manually pick one, so I'm going to click on the auto date range. Last year. Apply, and you can see without any SQL, it's just a very fast UI-based way of exploring your data. Hovering over, you can see the ferry building. There you go, 9,000 records, about 10,000 rides for just the year 2018. Great. So that's just an easy way that you can take a look at exploring common things right where your data lives. But if you're looking to build a fully fledged dashboard, you can save that, and essentially it promotes this one visual view. And what that's going to do is if you went over to Data Studio, that would then promote it as a dashboard that you have. So you have data sources, and then you have the reports. What I'm going to show you is a pre-built report that everyone has for Acme Marketing, just to highlight some of the key things that you can do inside of Data Studio. We'll use this template. We'll agree to the terms and conditions. We'll agree to helping Data Studio get better. And use the template. We're going to make a copy of this report. We're going to authenticate. And one of my favorite outages here at Google is good artists copy, great artists steal. And that's exactly what I tend to do with when I find a nice visual dashboard. So it's pretty trivial. Obviously, you don't get access to the underlying data source unless it's a public one, like the ones that we're doing now. But you just get a copy of a dashboard. So if someone's done something amazing with like geospatial visualization or these cool little up-down arrows based on the trend that you see here, and you want to know how you set that up, you can essentially just make a copy of that dashboard and then edit at your leisure without worrying about breaking their production dashboard. So just a few things I wanted to highlight in here that you saw a little bit earlier in the lecture. The first thing is you always want to be cognizant of what the viewer is going to see. So I'm constantly toggling back between the view, looking at my dashboard, seeing the insights. In this particular case, this is just Google Analytics visualized on a dashboard. So most of our pages are coming from organic search for this just example marketing website, and then referrals. So you want to be conscious of what the environment is going to look like for the user, whatever your target audience is. And then you can take a look at adding things like compacting the numbers. So if you wanted to show instead of 385,000, that's way too much, you could actually say the K or even like down to the millions and that sort of thing as well. So depending upon your users, you may want to aggregate so you're not showing them too much of granularity. Filters are great too, because what you can do is you can adjust naturally any of the style, but you can also specify a default date range. So if you want to zoom in on, say, you have a report that runs every week, you can set up to actually have a scheduled email to deliver that as a PDF for folks. But if you want, when people arrive at the report, just to have the last weeks of data and don't want to have them actually mess around with the filtering, you can do that by setting up the date range. So it's like an auto date range. So you could say, let's just say last week, and we're going to say start Sunday or something like that, and then automatically apply it. I don't know how recent this data source goes. Oh, wow, it actually does. It has until today. That's really cool. So you can see this data, I think, is live connected to a Google Analytics account. So you can see the session transfer last week, and then now this is defaulted from this view. So every time people go here, they'll have the blinders on or the restriction of just looking at last week's, and you can adjust it to last month's, whatever you want. So what I really like to do, honestly, is just create all the visuals first. You can mess around with which different chart types you want. So if you didn't want to have a time series, you could have the spark line, you could have many different options, and you can just click and it'll change that over time. I think the team that actually created this dashboard did a really good job, so I'm not going to mess around too much with what was here. But you can quickly change between those. You can add collaborators and share your report with folks, give them viewer permissions, editor permissions. You can add in nice different bars for just static HTML or regular rich text content. And honestly, the sky's the limit. What I would advise you to do is abide by what I like to call the data to ink ratio. And you see that even though we can dump a lot more metrics on this page, like fill up the white space here or maybe at the top, you don't want to overwhelm your visitors. So that's why a lot of the best reports that I see and that I recommend start with high-level KPIs or key performance indicators, obviously depending upon your use case, and then break down. They give you that title. It's imperative that you have a title and you're labeling your axes and your labels and just draw people's attention slowly. So maybe you start at the high level of detail and you're looking for the trends, which has a nice use of color here. And then you just scroll down and you get a little bit more of the detail as you scroll down the report. But that said, there's a ton of templates that exist out there for dashboards. You probably have experience building dashboards and other different tools. Take a look at Data Studio. It's very easy to connect to other different data sources, and you can create multiple different pages of your report if you want a different level of granularity, depending upon the user that's coming into there. But the best way to get experience with Data Studio is honestly just open up a dashboard, start creating new charts and see where it takes you. And the good news, I mean, normal things work here. So if you delete something and you want to undo or you want to redo, it's a very friendly platform. It's hard to break this type of thing. But that said, you need to have a good data set to bring in to visualize first. So you'll be spending a lot of time in BigQuery, creating those views, creating those tables that you actually want to report off of. And then the fun really begins when you get to visualize all that together. All right. Now it's time for you to put your skills to the test using all the tools that you just learned about. In this next lab, you'll be building an end-to-end streaming data pipeline to monitor your sensor data and then report on your data set in a near real-time fashion on a dashboard. The objectives for us are going to be, number one, set up a streaming topic inside of Cloud PubSub for subscribers to listen to. Number two, create a Dataflow job from a pre-existing template and then subscribe to that existing PubSub topic that you created earlier. Number three, run the job to stream all that data and monitor your Dataflow job as it outputs results into your sink, which in this case is going to be Google BigQuery, your data warehouse. Next, you'll analyze those results with SQL, and you'll create some views that you're going to use for visualizing the results later. Lastly, you'll be building a Data Studio dashboard to visualize those key metrics with Google Data Studio connecting to BigQuery as a data source. Keep in mind, you have multiple attempts at each lab, so if you don't get through it all the way on the first try, or if you want to come back later and experiment with it, you can always come back and start a new instance.
Hi, I'm Carolyn Ujic. I lead a team of machine learning engineers who have successfully implemented many machine learning projects across various industries. So far in this course, you've been applying machine learning to your structured data sets with custom models. It's time to widen our aperture and look at unstructured data sets, like images, and also other approaches to doing ML that don't involve custom model building. Here's our agenda. We'll first see how ML on unstructured data sets is driving value for businesses. Then, we'll look at the intuition and models behind unstructured data. After that is a critical topic on choosing the right ML approach, whether to build a model from scratch or use pre-existing building blocks. Lastly, we'll do a demo to classify text using 3 different approaches and compare the results. Here are just a few customer examples of companies who have used the ML tools on Google Cloud Platform on their datasets. The left-to-right ordering is reflective of more low-level programming to more abstraction and UI-based. Oknet built their own custom model to classify images of car parts and estimate price. Ocado used parsed results from the Natural Language API to route customer emails to the correct responders. Jiffy used the out-of-the-box Vision API to find the text in memes using optical character recognition. It then can reject inappropriate uploads based on sentiment or keywords. Uniqlo designed a shopping chatbot using the Dialogflow UI. Dialogflow is a Google-owned company which specializes in building ML-based interfaces, like intelligent chatbots. Let's look at some other use cases for ML in business. You might be Airbus and use machine learning to differentiate between clouds and snow cover. If you're stumped like I am, the clouds are in the upper right part of the right image, highlighted in red. You might be an economic forecast firm looking to track the global fleet of container ships via satellite imagery. Knowing the amount of cargo being carried might help improve your economic forecast by days or months ahead of the official numbers. Medical images are ripe for innovation. For example, you could diagnose medical conditions like diabetic retinopathy earlier when it's easier to treat and prevent blindness. The key takeaway is that ML can automate tasks that may save or assist a human team, and recently, the latest models are even outperforming humans in some domains. Also, image classification as a field is more than just binary classification tools.